flight.
Good evening and welcome to our retro stream tonight, a Super Stream Fighter. Firstly, I'd like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to the elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. Tonight, the ASV is proud to bring you our first interactive or fully interactive live stream. We have answered questions before, but we haven't done this before. We want you to join in selecting the objects that we live stack. Tonight, we ask you to take yourself back to the early 90s, to your local milk bar, 20-cent lolly bags, and throwing all your spare change into Super Street Fighter 2 as we embark on a journey deep into the universe and pit galaxy against galaxy, Nebula against Nebula, and planet against planet in this winner takes all stream. Which object will come out top in Super Stream Fighter? Voting is for Facebook only. So if you're on YouTube watching it and you do have Facebook, I'd say jump across to Facebook because it's the only platform we could get the voting to work on. We'll let you know when the voting happens, and you'll need to put your video in full screen to be able to see the voting options and select your object. But first, I will bring our stream team in. We have Andy, we have Neil with us tonight. Neil's very blocky. He's up in Cockatoo, so not having great fun with his connection by the looks of it there. We have Anne-Marie. We have Noel. I nearly called him Neil already. We have Claire, and we have Lee as well.
Evening.
So, good evening, everybody. Now, the first thing we're going to do while we're having a bit of a chatter is I'm going to put up our first post, our first poll. And the first poll is going to be the Centaurus A and the Sombrero Galaxy. And we'll leave the poll active. As I said, you've got to go into a full screen view to select. Once you select, you can exit full screen if you want to. We'll leave it active for a couple of minutes and then we will move to the winning object. So the poll is now active. I hope it says that it is. So people can start voting as to which one they want. Let's see. Oh, we've got some votes coming in. We do have some votes coming in. So now, while we're waiting, does anybody want to have a chat about some of the objects we're looking at tonight? We've got 11 battles on tonight. We have, first one up, as I said, is Centaurus A versus Sombrero Galaxy. Who wants to have what win tonight on our team here? Who's rooting for Sombrero and who's rooting for Centaurus A?
I'm definitely going Centaurus A, guys. That is my AGN. That is my radio galaxy right there. We don't do normal galaxies. Nuh-uh. We want galaxies that are, potential sites of other galaxies coming together and colliding. We want hungry, supermassive black holes. We want jets. We want excitement. We don't want boring old flat spiral galaxies that you can barely see anything. You can just see the dust lanes on the side, 6-degree inclination. Boring.
Well, we got a bit of
I've got to agree with Claire. Yeah. Centaurus A is a real stunner. It's unlike most galaxies that you'll see. The central dust lane has got structure in there that you can see with even small equipment. As Claire mentioned, it's an incredible radio source as well. If we could see in radio light, it'll be the brightest object in the night sky. It's just an amazing object, and it's relatively close to us as well.
All right, I think we are ready for the first poll. So the results I'm sharing on the video. Centaurus A won.
Yes!
Now,
I'm genuinely excited about Centaurus A.
For those of you who are on YouTube, you are actually able to comment now. I'm not sure what happened, but I fixed the setting and chat should be enabled on YouTube as well now. Now, who's going to stream across this? Actually, I can see some people already have streamed across. Look at that. Now,
Mark, got a request for you. Those of us who are watching through StreamYard, and I assume YouTube as well, won't be able to see the results from the Facebook polls. So would you be able to let us know?
That's what I said. Centaurus A won.
But what was the margin?
58% to 42%.
Oh, that was close.
Small
Closer than I
majority.
expected. Jeez.
Thank you for letting me know.
Now, what I'll do while we're talking about this object, I'm going to get the next poll going, which is Lobster Nebula versus Prawn Nebula, which is round 2. We're keeping them paired up as close as we can. So I forgot to say round 2, fight. So that poll is active while we talk about the object we've got in front of us, which is Centaurus A. So, Claire, would you like to chat a little bit more about Centaurus A since it's your pet galaxy?
Well, it's not my pet galaxy. It's my pet kind of galaxy because I like to study what we call active galactic nuclei. So deep in the center of galaxies, we think that there's a supermassive black hole. So usually between 1 million and 1 billion times the mass of our own sun. And these can be quiet and having a chilled out time, or they can be voracious matter consumers. And sometimes these engines, these internal engines, these black holes get really hungry because they get basically turned on, I suppose. They get smashed into by another galaxy. And that's what we suspect has happened here. It's a funny shaped galaxy. We're not really even sure whether it's what we call a lenticular galaxy, which is like a lentil shape, or if it's a giant elliptical. We're not really sure. But essentially, they think that this is actually caused by sort of two that are kind of coming together. You've got amazing jets of radiation coming out at sort of half the speed of light through the middle there. You've got these enormous dust lanes. It's a total mess of stars and lots of bits and pieces in there, but essentially it's the internal engine that makes me so excited, where all the gases and everything light up really close to the black hole because the material is just falling in at such an amazing rate. We're talking about 55 million solar masses at the center of this sort of weird lenticular giant mess of a galaxy. And one of the reasons it's really exciting is obviously when you've got two normal galaxies that come together and they've both got black holes, you can imagine what happens to the two black holes in the center eventually. So, when we're talking about two supermassive black holes that actually circle and eventually merge into one and produce gravitational waves. So there's actually a lot of physics just in this one galaxy, and so many different wavelengths that we can look at it, and so many ways that we can do science on this galaxy. That's why this particular galaxy, I think, is a better target than Sombrero.
Neil, care to add to that one? Well, he's on mute. You're muted.
Thank you for that. Yes. From an astrophotography perspective, which is my interest, Centaurus A is an amazing galaxy because it's big enough, bright enough, and close enough that we can really get some amazing images of it, as you can see here with what our members are showing you on screen. So just a reminder, these are all photos taken with amateur equipment by people who aren't being paid for their skills to do this. So it's amazing what incredible images you can get and what details you can reveal in this stunning galaxy. That the dust lane through the center there in particular is just remarkable to behold. I mean, you can see there in that zoom up image there how much structure there is that can be revealed in that dust lane. There are very, very few galaxies which present such an interesting dust lane that is as easily photographed as Centaurus A. So for that and all the other reasons that Claire has already mentioned, I would have to say that Centaurus A is one of my favorite galaxies in the night sky to photograph.
I think the other thing to consider is this is being live imaged at the moment. So this is Lee's being live imaging this one. So all the images we're seeing are from equipment being captured right now. Lee's out in Ringwood area. Andy's over, I I'm not sure where Andy is. He's out near the border somewhere out in South Australia. And Noel is up in Bendigo, and Anne-Marie is sort of towards sort of north, sort of central Victoria area. So they're all in different areas of Victoria live imaging these images for you at the moment. Now I'm going to go and check on the poll, and I might pause the poll now, and I will show the results. And for those who aren't on Facebook and can't see the poll and the results, Lobster Nebula slam dunked it, actually, 80% of the vote compared to Prawn. Poor old Prawn. He's been left in the dust. So now
we chucked that prawn on the Barbie.
Oh, we did. We chucked a prawn on the Barbie. I love it. Now I'm going to add.
Sorry, which one won? No, was it prawn or lobster? Sorry.
No, lobster won. Smashed it. Smashed prawn. Good. We threw the prawn on the Barbie.
Good.
So this is
Simone in the comments on Facebook actually makes a good point about Centaurus A, is that it is always up from our latitude. So it's always in the night sky.
Always up. Yes, it is. So now we are on good old lobster, and Noel is starting to live stack that. So what I will do for those on Facebook is I'll get the next poll going, which is Statue of Liberty Nebula versus the Running Chicken Nebula. And for that...
So which round is this, Mark?
Round 3, fight! The poll is active. I'm having too much fun with that, can you tell? Now, Neil, I'll let you start off on this one.
Okay, well, the prawn is an object that I personally have yet to try imaging, and I'm looking forward to giving that a go at some point. You can see that Noel here is fiddling around with the data that he's got, but it's only very early stages of his capture here. He's only got one frame so far. So as the time goes on and he collects more data, you'll be able to see him as he tweaks the display settings to give us a much better looking image. So we just need to give him a bit of time. But the Prawn Nebula is a large cluster or large collection of hydrogen gas that's visible towards the direction of the core of the Milky Way galaxy. And hydrogen is the most abundant element in the universe, so it makes sense that it is in most or pretty much all nebulae that we can see. And when it's illuminated by nearby stars, it actually glows in a pinkish red color. And you will see that once we've got enough data in here just to show that color. But that is the color of ionized hydrogen glowing, just like a fluorescent light tube glows when it's ionized by the electric current passing through it. We can start to see some of the color coming in there.
I've got Gavin asking where the vote button is. Gavin, you need to make your field of view in Facebook. You need to go to full screen, and it should pop up to allow you to vote yes or no for one or the other object.
So something's really about this is the Lobster Nebula, I think, and we think, or scientists believe, that they have some of the most massive stars that we know about are actually inside this nebula, and we don't really know why they're forming here. But it's really amazing. They're bright and they're blue and they're huge, absolutely enormous. There's actually an open cluster that sort of gives us the light. And there's a star in that has about 200 times the mass of our sun. These stars do not last long. They last, 1 million years or less. So we're pretty lucky that we aren't anywhere near those sorts of stars, because they're the ones that definitely go boom.
Big bada boom.
Yeah.
That's probably the wrong cultural reference, though. Maybe this one's going, Hadouken!
Fifth Element, we all know
it's from the 90s. It works. It works. It's there. Now, I'm going to close off the other poll and show the results. And the results are that everybody wants to see Lee's Running Chicken Nebula. So Lee,
I still can't see a running chicken in this nebula.
Lee has
I'm with you, Claire,
that he's drawn all over, and
that's not no. That's just one that sort of
it's you've been doing around.
It's been floating around. It's been doing the rounds.
Floating around.
So I'm actually having a bit of a. slewing problem at the moment. So.
That's okay. We can get the guys to move across to running chicken. And while they're doing that, we might jump across to the next one, which is...
Can I just make a suggestion, Mark?
Yep.
We're giving our photographers not a lot of time to collect data on these objects. So
I know.
Could we maybe make it 5 minutes at least for each object, so we can start to get something out of the noise?
At hand, young man. You need to have the information to share with everybody. So while
you told me I didn't need to prepare notes.
The next one we've got is Wishing Well Cluster versus Jewel Box Cluster, which is round 4, fight. So the poll is on Facebook while we move across to Running Chicken.
So can I ask, Mark, did people vote for Running Chicken over the Statue of Liberty Nebula?
They did, yes.
Oh, they missed out. The Statue of Liberty Nebula is absolutely beautiful. I don't know why people...
Stunning one.
Oh, it's gorgeous. Oh, I'm
because
disappointed.
the Running Chicken Nebula has got a hilarious name. That's probably why.
Oh, but the Statue of Liberty is just, stunning. It's got oxygen, sulfur, and bright stars and dust, and this amazing picture that we, like to do, where we sort of make pictures out of things. We recognize symbols where they aren't. Pareidolia, that's called. So, it's beautiful. It's actually gorgeous. And unlike the Running Chicken, I can actually see this Statue of Liberty in this nebula. So I'm shame on you, everybody that voted for Running Chicken, just because it has Bock globules, and I know you want to know about those. Yeah. Anyway, gosh.
I can show one of my photos of the Statue of Liberty as a consolation prize later on if folks are interested.
I think that might be a good one, but I'm going to make sure that everybody realizes that it's not the Statue of Liberty, that it's the Circle of Life Nebula.
What?
It looks like Simba is being raised up.
I don't think so. No, it's way more obvious that it's the Statue of Liberty. Oh.
I do like the irony that the Statue of Liberty Nebula is not visible from North America, though.
It's not, is it? Now,
it's the way it should be.
No, it's right near the Southern Cross.
Yeah, it's not visible for them. So how did they get the name Statue of Liberty then? If it's not near...
It looks like it.
Just because it looks like it, that's the only reason?
Well, why do you think the Sombrero Nebula? Why do you think the Sombrero Nebula is called? Why do you think the Sombrero Galaxy is called the Sombrero Galaxy?
Looks like a sombrero.
Right, there you go.
They should just be permanently called hamburger then, instead of just quietly referenced as hamburger.
Quietly referenced.
It's called Pareidolia. Just so you know.
That's what I said before. It's called Pareidolia when we see patterns in things like the face on Mars and Moon.
Sorry, I wasn't in the room.
No, that's okay. I've got this. I'll go out later.
And Mary and a grilled cheese sandwich.
Now we are waiting for Running Chicken to come up. We can't see it at the moment. Nobody's got it yet. So
in that case, I can put on Statue of Liberty.
Yes, do that. Show a statue. It's beautiful.
Statue of Liberty.
Oh, so it's also quite an exciting environment.
Now, just to give you a heads up, this is a what's called a false color image. The colors that you see here aren't natural colors, but they represent the distribution of different elements within the nebula.
Okay, here we go. We'll make this full screen as well, hey? Here it comes, slowly but surely. I've got a feeling that the internet for everybody around everywhere is running very slow because all of New South Wales is in lockdown and everyone's watching Netflix.
Mm-hmm. And Canberra.
And half of Victoria.
Why would we watch Canberra?
We're going to add Neil back into the stream. We've got 2 Neils.
Oh.
This was an issue. It was an issue we had the other night, didn't you? Didn't you?
Yeah, last night. For some reason, my browser might crash when I share a full screen image.
Here you go. Here we go. Now, if you can't see the circle of life with Simba being held up,
there's a head, there's the arm and the torch.
That's a Statue of Liberty.
And the cape coming down, standing on the platform.
Yeah, definitely.
Ignore the shapes of those stars. This was a couple of years ago when I hadn't got my telescope collimated correctly, but it's still a nice image. But the colors here represent different elements within the scene. So From memory, I believe I've made it so that the hydrogen elements are red, oxygen are blue, and sulfur are green. So we've got hydrogen in the background with oxygen in the foreground there, and that yellow patch out there is oxygen and sulfur together. Or is it hydrogen and sulfur? Yeah, hydrogen and sulfur together.
It's a beautiful image.
That is several hours worth of exposure, though.
I was just about to ask how many hours of exposure is that one?
That one, I believe, was about 12 hours. So don't expect what we can come up with tonight to look anything like these. This is the result of a lot of time imaging and processing the photo.
You and Anne-Marie have been hanging out, having the two of you do some seriously long exposures. But
exactly. When you've got really faint objects like the extremities of this nebula, the longer exposure time really helps bring that out.
What's really cool about this as well is you can see the sort of looping filaments of gas. So sort of where the torch is above the torch, you sort of see this like looping cloud. And all of this is sort of what's cool about this nebula is that you've got some really big, massive stars in there, young, massive stars, and so quite a few being born as well. And so when they are born, they sort of push out the gas from around them. And that whole area there, it's sort of windy. It's what we call a stellar wind and then interstellar wind. And so all that movement of gas basically from all the stars sort of creates these big looping filaments of gas. And that's actually kind of incredible to watch gas moving in such a large direction from single massive stars, just creating sort of wind tunnels essentially in space.
Now, I'm going to see if we got any of our boys got. Oh, here we go. The start of running chicken on Knowles.
How are we going with that other poll?
Oh, yes. Oh, I'm going to leave this one up a bit, only because I want to make sure that our Deep Sky section director's favourite one wins.
Oh, got to be doable.
No biasing the results, Mark. That's unfair.
No, I can't. That's the thing. I can't though. I can just leave it open for people to comment on. So we have here. Oh, this is Statue of Liberty that Noel is live stacking. Has anyone got running chicken? Because that's what won.
Everyone's rebelling against the results.
Yeah, we're rebelling.
Well, no, my scope was.
Is it back on?
I'm trying.
You're trying?
So, yeah.
It's almost like none of them want to go to running chicken.
the scope certainly didn't.
All right, while we're waiting, we're going to cheat, and we'll get Neil's version, which is how many hours?
Here's one I prepared earlier.
Here's one you prepared earlier. How many hours in that?
So, as you can see, there's a lot of the pink stuff here. So this is a true color image. The pink there and the purple is representing is illustrating where the distribution of hydrogen gas is. So Claire will be able to go into more detail about this, but the reason why we get gas glowing is because the energy from nearby stars gets absorbed by the atoms in that gas and dust. And the atoms aren't able to hold on to that energy, that extra energy for long. They're unstable. And so they'll spit that energy back out, but they can only do it at very specific wavelengths, specific frequencies. Hydrogen has three or more, but two major brightness levels that it will emit light at, and that is in the deep red and sort of a tealy blue color. And when those two are emitted together, you get this combination of pinks and sort of grey pinks and purples that you can see going through the image here. The bright star on the right there is Lambda Centauri, that is in the constellation of Centaurus. And this is, as we said, is called the running chicken. Now, everyone sees a chicken differently in here or doesn't see it at all. I
just saw it.
I see here we've got the eye, and we've got a beak down here open out and sort of clucking. We've got the comb on its head up the top here and the body coming around the back with its wing up behind it. That's the way I see it. Is that what you saw, Claire?
I couldn't really see your cursor except when it was very close to that star, but you're talking about the very big star, aren't you? That's the eye, and then the beak is to the right.
Yes.
Is that correct? Yeah, I can see it now. It's nice and slow.
seeing
And the comb on the
beak
top.
down
I
here.
see it. Yeah. And then the sort of curve on the left there is like the fluffy bum with the little feathers out the back.
That's what I see, yes.
Me too. Great. I've seen it.
I do think, though, that it depends a lot on what image you've taken. So if it's a different exposure setting or different wavelengths the imaging, people see chickens in different ways.
So we do have a live stack of it coming in now, slowly but surely. Lee, can I ask you if you can find that image that you shared in the in our little live stream chat group earlier? I reckon we should show everybody that, because it perfectly identifies what Neil was talking about. While we wait for for Noel to live stack some more images, here it is. So we've got 2 frames at 60 seconds per exposure. This is 1 minute 20. And how long was yours, Neil?
No, that's 60 seconds total exposure, Mark.
Oh,
so they're 30-second exposures.
Oh, and how long was yours?
Oh, mine? That was about 4 hours.
There you go. There's a difference, isn't it? So I think if we get Lee's photo, people will understand what we're talking about when we say running chicken.
Definitely. I just got there's a couple of things. Things are crashy for some reason.
I had a friend refer to it as the run over chicken, and I think that's a bit more descriptive of it.
Oh.
It definitely looks like a squash chook rather than a one that's running around on its hind legs.
There you go.
Yeah, that's not what I see at all.
No, that's a different one from what I said.
That is a different way, isn't it? There we go.
Yep. So as I said, everyone sees it differently.
I could see the one that you were talking about, Neil, but I can also see this one.
There's another one as well. Hang on. Let me just unshare that one. There's always this one here. I have no idea who's brought
it. Doesn't look like it's running.
Okay.
No. A remonstrating chicken.
Yeah, I was going to say more like a fed-up chicken. I'm fed up. I'm out of here.
Stop asking me why I crossed the road.
We're all having internet issues tonight because the YouTube one, for some reason, it's not allowing chat, even though I've reset everything. It's very odd.
Instead of chat, people can use the comments instead, and they'll come through to us.
Yeah, they can use the comments if they want to, but for some reason it's just not allowing chat, and I don't know why. I've changed all the settings, but I can't get it to work. So we're in live stream limbo at the moment. It's very, very interesting. So I'm going to go back to
do it live.
Here we go. We have 3 minutes of data at the moment on the running chicken now.
That's starting to look good.
There we go. It is starting to come together. Now I'm going to go and check the results of the next one while we're waiting for this to load up.
All right, you go check that, Mark. I'm going to just say that what's really cool about running chicken is something called Bock globules, which is kind of funny because, it's running chicken and it's Bock, Bock, Bock. But that's not actually named after the nebula or anything like that, or the galaxy like that. It's actually named after Bart Jan Bock. And they're basically these dark masses, and we're still not 100% sure what they are, but we think that they are areas of intense star formation. The interesting thing about running chicken is that so some astrophysicists had a look at the data, and they actually don't think there's any star formation going on in these Bock globules. And these Bock globules actually look like, when you zoom in, they look like they're kind of being shredded apart. So either it's an unusual situation here, or we don't really understand anything about them, which I think is absolutely fantastic.
Now we have the results in for the next target. I'm about to share them, and I will say that our Deep Sky section director is going to be very happy because Jawbox won 67% to 33%.
How many times did he vote?
Oh, I probably voted a lot, I reckon. I think you must have voted quite a few times.
He's got 60 accounts and he logged into all of them. And
Of course, we're being sarcastic here. Paul doesn't love the jewel box cluster
at all. Hates it.
Well, it's not so much that he hates it, but he hates that it's the one that everyone knows and what they request to look at.
What's the next one that they're voting for, Mark, if we're starting to look at the jewel box?
Oh, you'll have to wait. I'll get that one going. Close the results. Just quickly, those watching on YouTube, if they refresh their stream, they should be able to put comments up. I've got a few people messaging me about to let you guys know that. So do apologise. I'm jumping between about 4 screens at the moment, trying to get those comments working for everybody. So I think we've fixed it. So if you refresh your YouTube stream, you should be able to put comments up now. Now, while we move to jewel box and get that one set up, I suppose we should go to the next vote, which is for round 5, which is Omega Centauri versus 47 Tucanae. And it is round 5, fight! And poll is active. Start voting. Get the voting going. Now, have we got anybody on jewel box? Not sure if anyone's moved across to jewel box.
It'll take a little time for everyone to slew over there and start getting their data.
I was struggling as it was to get the chicken. I eventually did. That's the chicken right there. But
yeah. Here we go. Well, I'm going to chuck Andy's up. I'll put us back on screen for the moment so everyone can see our lovely faces. And Andy said about 20 seconds and he should have... Oh, it dinged in my ear again. Do you know what that means? That means somebody gave us stars again. I thank you very much to those on Facebook who are donating stars. Every star helps. Every star helps.
It's you who are the real stars, folks.
That is spot on, Neil. It is the people donating stars who are stars.
Oh, Neil.
So thank you. Thank you. You'd think.
I know. Yeah, I do like the cliches.
That was dad joke. Yes, that was.
Yeah.
Gunnar has donated 99 stars. We've had Chris Naylor donate.
Oh, thank you, Gunnar.
Stars. Thank you. And tonight we've had, there was somebody else. I can't see it anymore.
It's coming.
That's not Gunnar, who I
It's a bit
know
slow.
to
Screen from screen to screen.
What was that, Lee?
I seem to recall seeing somewhere Gunnar, if it's the same Gunnar, is around 80 years old.
Yes, and yes.
Was a previous council member and
yes.
I was friends with Gunnar when I joined the ASV at age 16. I am now 46.
How old are you? 21?
Yeah, that's right.
Do we all have to tell our ages?
No,
25th anniversary.
I don't want to make Gunnar feel old, though, so sorry about that, Gunnar.
All right, we have our first stacked image coming through of jewel box.
60 seconds. That's all it is. I'm just doing a quick 60-second images, and I've got it stacking, so it's loading and stacking.
So who'd like to start talking about jewel box? Don't everyone jump in at once. This is where we need Paul, Deep Sky Section Director. He could tell us all about that.
So the jewel box is what we call an open cluster. So a cluster of stars, of course, and an open cluster is a type of star cluster that's made up of usually a few thousand stars, and they generally are formed from the same giant molecular cloud that's collapsed. So you have this cold molecular cloud in space, and then it starts to collapse. Usually gets a little nudge from something gravitational, or it can have like something going off nearby, like a supernova or something, and it will actually induce the cloud to collapse. I'm getting a lot of feedback. So it induces the cloud to collapse into these stars, and so these stars typically have a sort of similar age, and that's why we can sort of use open clusters to sort of map out the age of certain parts of our galaxy. And so the jewel box is absolutely beautiful, and it's called the jewel box if you've ever looked at it, particularly pictures of it. After a long time, some exposure, you start to get colors come through, and you get some beautiful red giant colors coming through, and you've got these bright blue hot stars as well, and it just looks like a glittering box of jewels.
I had it told to me when I first saw it that it's like someone has spilled jewels across a glass table.
Well, I don't have a glass table, and I certainly do not have a box of jewels, so I can't comment on that. But I'm open to people sending me those things. They can do that.
Yeah. There you go. You've heard
Send
it
to
here.
Claire Canyon, PO Box.
Send me jewelry.
If you'd like to send Claire jewelry, she will accept it.
I will take a photo of me spreading it across a glass table, and I'll post it. I'm happy to do that for you.
Now, Neil, you'll be happy to know that Gunnar doesn't feel old.
There you
I
go.
saw that. Good on you, Gunnar. You're a legend.
And Neil, do you have anything to add to the jewel box while I check the voting on
only my photo, which is in the shared screens queue, if you wanted to put that up.
Oh, so there's a question from Jamie, which I wouldn't mind just commenting on. So Jamie said, does the redshift in some stars in the cluster mean they're quite old? So redshift is usually something we use that describes movement or motion. So when we talk about redshift, you can think about an ambulance coming towards you, hopefully not at you, or away from you. And when it's traveling towards you, the sound sort of waves bunch up and it becomes a higher pitch or a higher frequency. And when it's moving away, it becomes a lower frequency. And so if you were to do that with light, for example, a star coming towards you, hopefully not at you again, it's actually going to have light that gets shifted to the blue. So the higher frequencies are bluer. And when the stars are moving away, it gets shifted towards the red. So the light actually appears redder than it was when it was emitted. Now, these stars actually aren't, they're all together, so they're not really moving with respect to each other, and that's not why they look red and blue. The blue and the red is actually their colors. So red stars are typically cooler, and blue stars tend to be hotter. Just like when you heat up a piece of metal, it goes through the sort of red to the yellow phase, and then when it's blue, white, burning hot, you definitely don't want to go anywhere near it, and you can actually feel the heat from a long, long way away. So it's the same sort of scale. Red to blue is cooler to hotter, and yeah, it's not necessarily to do with redshift. It's more just the actual color of the light that's coming to that's reaching our eyes.
That's a really good answer, Matt. I think that's sort of cleared it up quite nicely.
Oh, thank you.
Before we jump to the next one, Neil, I'm trying to share your screen. There it is. This is Neil's jewel box. And then I'll share Noel's jewel box. Noel's has got a bigger jewel box. And this is Noel's. Look at that. Nice and deep and right in there.
And I have to say something, David's made a comment here about blue and redshift not being visible to the naked eye. That's mostly true, except I don't deal with any sort of visual so images at all. And it's not actually necessarily true. There's very, very deep Hubble images. I suppose that's not naked eye, but it's certainly a camera, where we can see reddened galaxies. But I actually deal with spectra. So I can actually, when I look at the way that the wavelength and the flux, when you plot them together, when I look at particular lines, I can tell usually if I know what I'm looking for, redshifts of very small amounts. So, 0.1, 0.0 values in spectra will tell us whether things are moving towards or away from us, even a little bit for the time being. So we can actually do that with galaxies as well. We can work out their rotations by looking at their spectra, but certainly not, as you said, certainly not, David, as, using actual blue and red colors that we see with our eyes.
Okay, so I think we might go and check on that poll, see where we're at. I think we've got an answer to the poll on this one. I will pause that poll and I will show the results. Then for the people on StreamYard with me and for those on YouTube watching and Twitch, Omega Centauri won it 58% to 42%. So the guys want to start jumping across to Omega Centauri. We can start streaming that, and we might jump across to Knowles while he's jumped back to his image. I was going to show everyone while you were slewing across to Omega. So this is Knowles' system. He's slewing it across and he's going to start. But we do have a question, Claire. What's a redshift? Oh, I can't hear you, Claire. Your sound's gone.
That's okay. I clicked mute on my fancy microphone.
Fancy.
It was going to happen at least once tonight. There it is. So redshift is what we normally talk about. We can do with light. We say red for light because basically every wavelength has a number. It's a number of waves that pass. It's the length of a wave. Or for frequency, it's how many wave peaks go past per second. So if you're standing on a pier, the frequency would be how many waves go past in 1 second, and the wavelength is the distance between one peak to the other. So when we talk about redshift and blueshift, what that means is when things are red shifted, it means that the light that they actually emit at the source, so a star, for example, if the star is moving away from us, what happens is that the movement away combines with the wavelength of the actual wave emitted on its way to us. And so it's actually a further distance, kind of almost than the light thought it was going to have to travel, which means that the light actually, when it gets to us, is actually got a longer wavelength. So it's a redder color, I suppose, but light goes all the way down past colors. So things with long wavelengths are redder, things with shorter wavelengths are bluer. And so we call it a red shift because if it's moving away, the actual color it emitted has actually, when we see it, has actually shifted closer to the red colors. If it's coming towards us and it emits, let's say, green light, if it's coming towards us, it does what's called a blue shift. Because of the proper motion, so the motion coming towards us, that means that sort of all the wavelengths bunch up on the way to us, and we actually see a higher wavelength, a shorter wavelength, a higher frequency, and the light looks a bit bluer. So if it emitted green light and it's coming towards us, it might actually look blue to us. So we can sort of, if we know what light was already emitted, we can kind of work out what speed it's coming towards us, or if it's redder, how fast it's actually moving away from us. So that's a red shift. You can hear it with ambulances. So if it's coming towards you and it's getting higher and higher and higher, it's getting the equivalent of blue shift. It's called a Doppler shift. And if it's getting lower and lower and lower in sound, so the pitch is going down, it's getting lower in pitch. So lower in pitch is like down here, and higher in pitch is up there. And when something's moving away, things go lower and lower and lower pitch. So that's the same as a redshift for light.
Very detailed answer. That went straight over my head. I won't pretend to say that I know anything about what you just spoke of. No, I know some of it.
Well, that's concerning.
No, I know what you're talking about. I'm just being cheeky. Now, next poll, while the boys start imaging Omega Centauri, is the Lagoon Nebula versus Triford Nebula, and that is round 6, fight. Poll is active. Start voting. Facebook votes only, obviously. So if you are able to jump on Facebook, jump on and try and vote for this one. We'll leave this up while we start to talk about Omega Centauri, which we've got on our screen already. Neil, I'm going to throw this one to you.
Yeah, no problem. This is a stunning object. It's called a globular cluster, and I suppose looking at it, the reason for that designation is quite obvious. It is a cluster of stars which have come together under their own mutual gravitational attraction into a globe shape. These objects are usually located near but not in the galaxy. They orbit around the Milky Way galaxy, and there are hundreds of them, but what we're looking at here is by far the largest. So most globular clusters will have several tens of thousands to hundreds of thousands of stars in it. Omega Centauri, however, has over 10 million stars in it. It is an absolute monster. It's so big and bright, in fact, that you can actually see it as a blurry star to the naked eye from a good, even moderately light polluted skies. Because this is such a big globular cluster, there has been discussion as to whether it may be the core of a previously larger galaxy that was too close to our Milky Way galaxy and had the outer stars ripped off and absorbed into the Milky Way, leaving behind only those stars which were so close to each other in the core that their mutual gravitation were able to resist being pulled into the Milky Way. That would explain why this one is so much larger than the next largest, which is about 1/10 of the size. This looks gorgeous through a telescope. Just about any size telescope will show beautiful stars. And I think it's one of those objects that almost always will look better through a telescope than it does in photos. Most nebulae will look better in photos no matter what. But a cluster like this, the experience, the sensation of just seeing these pinpoint sparkles of light is just unparalleled to what you can get in a camera. It really has almost a three-dimensional feeling to it when you look at it with your own eyes. So as an astrophotographer, I will say, if you've got a telescope of any size, get out there and try and find this object, and you will be amazed what you see through a telescope.
Now, Claire, there is a question for you that relates to stars, which we're looking at in this, but also galaxies. So with what you were talking about earlier, can that help figuring out the age of a star or a galaxy? And continuing on
yes
from Redshift
and no. Yes and no. So generally when we talk about redshift and blueshift, we literally are trying to say it's coming towards us or going away from us. Well, actually the other way around, if you want to do it in the order I just said. So if it's got a red shift, it's moving away from us looking at it. And if it's got a blue shift, the object is moving towards us. So that's actually nothing to do with necessarily the color that is being emitted by those stars. And as I was saying before, typically when we're looking at stars, it's the red colored stars that are cooler and the blue colored stars that are higher temperature. So typically colors mean a little bit more about the internal workings of what we're looking at, and that redshift and the blueshift refer to its motion towards or away from us. I've got to stop saying them in reverse order. So the redshift and the blueshift are about whether the star is going away or towards us or galaxy. However, in an interesting little thing that, well, there's another type of redshift that's called cosmological redshift. And this is going to blow your mind maybe a little bit. So it's not actually related to Doppler. It's not about waves traveling through space. It's actually about, and getting bunched up because of the movement, it's actually about space expanding in between the object and us. So when we look out, particularly at objects that are a long way away, we actually see light that has been stretched as the space in between has been made. So as the universe expands, it's not that objects are moving through space away from each other. It's actually that space in between is growing, which is, I think, crazy. I find that so hard. I mean, human beings are, we think about time as sort of linear, and 3D is something we can touch and feel. And the whole idea of 4D space-time and space just expanding in between is incredible. But so that's a type of redshift called cosmological redshift. And that actually causes pretty much all the galaxies we can see very, very far away to be a lot redder. The light that we get at Earth to be a lot redder than they probably was when it was emitted. But that's, as I said, because the space is being made in between, sort of effectively stretching the wavelength. So using that information with those galaxies, we can actually if we know a little bit about what we think the universe is doing in terms of its rate of expansion, you can sort of backtrack and infer the age of the universe, and certainly the age of the sort of things that you're looking at. So it was probably an accidental yes there, but yeah, so no and yes. And Jamie, I'm really glad that blew your mind. It blows mine too, and I deal with it every day.
You're dealing with it every day and you're still amazed by it. Now I'm going to go and check the poll, and it's another runaway. I might leave it just for a little bit longer in case we've got anything else we'd like to add to this. We have had a request for 47 Tuck, but it lost, so I'm going to be a nasty host and say no for now. Maybe when we finished our group of our rounds, we might come back to it.
I can probably add something to this if you like, Mark. This, if you want to, if you haven't heard enough of my voice, my dulcet tones. Omega Centauri, actually. So some of the data I work with comes from a telescope. There's two telescopes in this pairing, I suppose. And the telescope's observatory is called Gemini, which is, twins. And one of them's in Hawaii and the other one is in Cerro Porchon in Chile. And my data actually comes from there. So the sort of quasars, the AGN that I look at and sort of look at the spectra every day and try to work out what the gases around the black holes doing, that's where my data comes from. But they're actually at the same observatory in Cerro Porchon in Chile on this Gemini telescope called Gemini South. They actually looked at Omega Centauri, and because it is so massive, there was sort of as Noel, I said Noel. Oh, Neil, don't hurt me. As Neil said, I didn't think I was ever going to get that wrong.
That's my job. It's my job to get it wrong. All right.
I'm sorry, Neil. So Neil,
don't worry, I'm used to it.
Oh, no, don't be. If you put an I in my name, I will kill you. So if you put an O, I'll just be confused. So anyway, Omega Centauri is so big that they thought, oh, maybe it is the core of a dwarf galaxy and it's had its sort of outer parts stripped away. And so they, with this telescope, this Gemini South, they had a good look at the stars, and they used Redshift to work out the motions of all the stars, well, not all of them, but some of the stars from the outside of the cluster into the center of the cluster. And that sort of, they sort of inferred that potentially there's a mass in the middle that's making all of these stars sort of rotate around with a speed that is what's the sign? Oh, what's the word? Proportional to their distance from the outside and inside. So if you think about the solar system, right, you've got the planets out the back are sort of like shooting around. The ones that are very far away and the ones that are inside are sort of like going around as well, but they can't go at the same speed, otherwise it'd be crazy. So there's a proportionality, and that sort of suggests that there's a big mass in the middle. However, when other researchers looked at it, they actually weren't sure that they could find stars that in fact did obey this proportionality law. So it's still really, really unclear as to whether there is a black hole in the center. It's probably not a supermassive black hole, for 40,000 solar masses. So at any rate, it should be what we call an intermediate black hole, which has really only just been sort of confirmed in the last few years. There's only a couple of sources that we think we've sort of can say that they are intermediate mass black holes. So it's just really unusual and still an amazing enigma that, I think is amazing that we can even ask these questions and find data to support it, let alone come up with a definitive answer.
That's a very detailed answer, and hopefully they understood that. We do have another question that I'm going to get to in a second, but first I'm going to... Yes?
Just want to interrupt you there and say, don't necessarily think that our audience aren't up to understanding these amazing answers from Claire. Just because you struggle to answer doesn't mean everyone else does.
Well, that's true. I'm not the sharpest tool in the cookie jar. Now, it's time for the results of our next poll. And that was Lagoon versus Triford. And the results are in. It was a 39% for Lagoon and 61% for Triford. And I'm excited about that because I am a huge Triford Nebula fan. I've been trying to image it from my backyard with my phone all through all of these lockdowns. and I just haven't been able to get it yet. So, I do love the look of it. Now, what I'm going to do is get the next poll going, and then Neil has an answer to the next question that's been posted, which we'll get to. But the next round is Helix Nebula versus Dumbbell Nebula, which is round 7. Fight! Poll is active. Now, the question was, what direction are the stars moving in the globular cluster? And I'm going to give Noel his screen back and jump to Neil's screen. And Neil has a video that can answer that.
So yes, as you can see here, this is a simulation of a small cluster. To simulate the movement of all stars interacting with all other stars takes a huge amount of computing power. So we're not going to be able to get a simulation of 10 million stars in a globular cluster. But this is a relatively good small-scale representation of the kind of chaos that is going on inside these things. Every star, of course, influences the movement of every other star because all forces, all masses in the universe attract each other with their gravitational pulls, and they're all in motion. There's no such thing as a static thing in the universe. Everything is in motion relative to something else. And so what you end up with is this kind of, bee swarm of movement going on, all sort of averaged around a central point, which is sort of the center of mass of the globular cluster or the star cluster. And these things are always in movement. Now, occasionally you'll get stars that come very, very close to each other, and you'll see what we call the slingshot effect, where one or more stars pass so close to each other that they actually accelerate the other star in tremendous speeds and may even throw it out of the cluster. The same thing happens with any mass bodies. So planets as well can be flung out of their respective solar systems, and astronomers are now speculating that perhaps there might be hundreds of billions of lone planets out there between stars that have been ejected at some point in their life existence from their stellar systems. So as to the question of what direction the star's moving, generally they're moving all over the place, but it may be that over time the average movement is in a sort of a clockwise or an anti-clockwise direction, depending on the angle that you're looking at it from. These things do often seem to average out. If there's 51% of stars moving roughly anti-clockwise, then they will slowly drag around the other 49%. They'll lose speed, but the average rotational orientation will start to line up over time, but not always. So that is something that is very hard to analyze because these stars are all moving, but we're only seeing them in a very short period of their lifetime. So it's very hard to know exactly where and how fast they're moving. But our simulations like this one really do help to shed light onto that process.
I love that video. It was really cool. Oh, we've lost.
It really is, isn't it? It's mesmerizing.
It's very mesmerizing. We jump across to Lee's screen here. He's got 60 seconds worth on Triford at the moment. So Claire, I'm going to let you have a chat about Triford, and Neil, I know you're a huge fan of Triford as well.
I am.
Oh,
You should let. No, I caught myself. There's no need to tell the entire world through the internet, Mark.
There is. When you forget to unmute yourself, there absolutely is.
Nobody noticed,
We did.
Nobody noticed. Did you, world? Comment if you actually noticed. A little love over this way, thank you. Neil, I'm happy for you to take away this. I personally just absolutely love this as an image. I seriously just want to get the Hubble, the HST images and just blow it up and put it on my wall. It's absolutely beautiful. So Neil, I'm going to let you talk about it because it's your favorite.
Thank you, Claire. I couldn't agree with you more. I think of all the nebulae in the night sky, I think the Triford Nebula is probably one of the most arresting to look at. It's one of the most interesting because it shows a lot of different astronomical processes in the same object. I think graphically it's very interesting because it's got a nice symmetry. It's also got the dividing lines running through the nebula. It's just an absolutely beautiful object. One of the greater things about it is the color difference. We talked earlier about pink nebulae being hydrogen emitting light, but we've also got, you can see it in the bottom there, we've got a blue nebula. Now that is not emitting that light, it is reflecting it. So when the energy of the nearby stars, and Claire will probably be able to confirm this for me, but when it's at a certain level, it will excite the atoms and cause them to glow, to fluoresce. But when it's not quite strong enough for the atoms to absorb it, they will instead reflect it. The light will bounce off it. And in that case, the dust and the gas takes on the color of the stars nearby. So we're seeing here the same gas and material in between these two different colors, but they're looking at different colors because of the amount of energy that they're either absorbing and re-emitting or reflecting. Just like putting a blue torch into fog, we're getting blue light bouncing off that fog. It's a moderately large object. It will fit in the field of view of most telescopes. It's smaller, certainly, compared to the Lagoon Nebula, which is the nearby neighbor. But that means that you can get a nice composition that fits the whole thing in the frame, and so that looks quite striking. Once we've had a look at the photos here from our members who are imaging live, I've got a photo that I've taken of it in the past that we can perhaps compare what you get when you dedicate several hours to collecting the light from this beautiful object as a comparison. But Claire, do you have anything on the astronomical side of things to add to it beyond the astrophotography?
So this is what we call a stellar nursery. So earlier I was talking about molecular clouds having to be cold. And the reason they have to be cold is because when gas is warm, the particles are basically flying around. So another way we can think about temperature is actually velocity of the particles of gas. So when we have a high temperature, the gas particles are flying around, and the last thing they want to do is get together. So in a cold gas, in these stellar nurseries where there's sort of little dust pieces and cold gas, the gas is actually moving quite slowly. So it comes up to another piece of gas and says, hey, let's get together. And eventually what happens is there's enough gas, particles and dust that it actually just starts to gravitationally collapse. And so that's why these stellar nurseries are often so beautiful, because they have these dust lanes, big areas of dust that absorb the light coming through. They're illuminated, as Neil was saying, by these young stars, which we call embryonic stars. So it's the stars in their very first stages of life. It's absolutely beautiful. And then it's absolutely gorgeous. So you've got your dust, you've got your stars, and actually one of my favorite little areas is that top space where it's kind of like dusty. That's the part that I call the bug, and it's got this like these stems coming out, these little antler areas. Actually you're zooming in on it perfectly. It's just above the really bright stars in the center. And when you look at Hubble space images of this one particularly, they zoom right in on that area, and you can actually see, you get this real idea of how dusty it is in there, and all these particles of material that are sitting there, and then there's this beam of light just coming out of the gas. It looks like that. You can see the sort of two little antennae there, and so they're actually jets of light.
Is this that little snail slug looking thing?
Yeah, it's the little snail with the antennae, and the antennae actually are the jets from the star that's just ignited, and it's blowing out stellar winds, like I was talking about earlier when we talked about those gas loops that were in the Statue of Liberty Nebula. So these stars ignite, and they blow these fierce stellar winds, and they blow back the gas and the dust around the star once they ignite. But what's really cool here is that the dust is so dense that it kind of blocks being blown away, and where it sort of comes out as a pillar, a jet, is actually where the gas is actually sort of protruded. That's it. That's perfectly. So that's a stellar jet. So there's a little star there that's just blown away the dust, but there's a bit of area where the dust is just too much and it can't really blow through it. So I find this nebula is so beautiful from a macro perspective, looking back at all the colors like Neil was explaining, but also just from the astrophysical processes going on in there are absolutely beautiful.
Amazing live stack there, Lee.
Thank you.
Now, Neil, I know you're going to share your image, but I've been asked separately to share an image of somebody's. And
Go for it.
know, because he heard that you were sharing yours, so he sent it to me and said, share mine as well. So I will.
Please do. It's not the Neil show here. I want to make sure everyone's getting their amazing photos seen.
Just bear with me. I'm going to have to open it up into good old photos. Let's see if I can get it to work now. Actually, I'll share yours while I'm looking for mine. So this is your one, yeah. Sorry, not
That's
mine.
right.
The one I was sent. I love yours. Yours is absolutely stunning, and just the contrast in the colors is amazing in this image.
Thank you very much. I put a lot of work to get that contrast and that saturation like that. One of the questions that I'm often asked is it really that color? And it's a difficult question to answer because there's no real simple answer to that. The color you're seeing here is accurate to what a human eye would see if we could see incredibly, incredibly faint things, much fainter than we are actually able to. But the contrast and the saturation have been exaggerated to enhance those colors and enhance the difference between them. But if we were to look at that object from a spaceship from a dozen light years away from it, it would barely be visible at all to our eyes because these things are so incredibly faint. This is several hours worth of exposure, and being closer to it wouldn't make that much difference because you are getting more light because you're closer, but the object would appear much larger in your field of view. Therefore, that light is spread out over a larger part of the sky. So if you were inside the nebula, you wouldn't even necessarily know about it. The glow that you are seeing here is not something that is glowing that bright actually inside it. So you could be inside a nebula and not realize that you were. In fact, I read that there was recent papers published that suggest that the Earth in the solar system is actually inside a moderately bright nebula itself. And we can't tell because it's very difficult to distinguish the background brightness of the night sky from what might be the glowing of gas that's surrounding us completely. And of course, Diego's photo is absolutely stunning here. Diego is one of the ASV's best photographers, and you really did have to set me up, didn't you, Mark, putting his photo after mine.
I? Sorry, I couldn't resist. He's been sending me.
Diego is a master, and he's someone that I look up to and aspire to reach that quality of work.
I've got to say that I think both your image and his image are both as good as each other's, if I'm being perfectly honest. I like the two of them. They're both. His shows off more of the red. Yours shows off more of the blue.
Well, thank you very much, Mark. This sort of thing is as much an art as it is a science. And so the subjectivity is in the creation of it and also in the appreciation of it. So different people will like other people's work differently. So I think it's important that we do try and show as many different interpretations of these objects as we can, because there is no one right way to do it.
That is true. Now, I think we should check the poll for round 7. And Dumbbell, I'm sorry to say, has been hit for 6 by the Helix Nebula, which has smashed it out of the park. Is 70% of the vote for the Helix Nebula. Show the results there for those on Facebook. And Dumbbell got 30% of the votes. Now, while the guys start getting their stacking ready, we will get the next poll going, which I think everyone will be excited about. The next one is Saturn versus Jupiter, and it is round 8 fight. Poll is live. So let's jump across. Whoops. Let's jump across to, I think I can see. Well, there we go. Let's look at this. This is Noel's version of Helix Nebula. He's got it going nicely there. Now, Claire, I will let you start with this one because Neil finished off on the last one, so it's your turn to start, I think. Just got to try and unmute again, I bet you.
No, I was looking for my tab. Thank you very much.
Tab. That is so
Well,
80s.
No, because listen, because StreamYard doesn't really like Firefox, you see, and I don't use Chrome a lot, so I had to find my window for Chrome and then find the right tab, you see. Yes. Anyway, so the Helix Nebula is a different kind of nebula than what we've talked about so far tonight. It's what we call a planetary nebula, but it actually has nothing to do with planets. So odd name, definitely. Basically, what you're looking at there is there's a star in the middle that has got to be a red giant, so not a big massive star, more like a star kind of like our sun's mass, which will never be a supernova. It's never going to be that exciting. It's just living out its nice long working life and then dying. So these stars of this size, basically they become a red giant, and then the outer layers puff off into space in this sort of ionized material. So what you're actually seeing there, the rings, and this is why these planetary nebulae often have these sort of ring or round shapes, is because they puff away from the surface as the star actually can't really hold on to its outer layers anymore. And it's absolutely beautiful. It just glows like an eyeball. I absolutely love this nebula. So we actually, the sun itself, after it's become a red giant and potentially swallowed up Earth and gone to Mars's orbit, after that it'll start some helium. So it starts helium burning. There's a bit of wobbling, and then eventually it just can't really hold on to the outer layers anymore. And the sun itself, our sun, may actually make a beautiful planetary nebula, which, if we're around somewhere else on another far distant planet or in a spaceship somewhere, we may one day look back and look at our own sun's planetary nebula.
Now, I think what Jamie's trying to say is that the Helix Nebula is a forbidden lifesaver, maybe? Kind of does look like a forbidden lifesaver, doesn't it?
As in lifesaver, like the lollies? The sweets?
Yes, it kind of does look like one of those. Neil, just so that Neil deGrasse Tyson would be proud, Neil. So, and Cigar, there you go. I'm not ignoring YouTube comments.
That is a lovely
I was
comment.
definitely going to say that. Yeah, Sagar's been really, really active, and you've just ignored him the whole time, Mark. You're so mean.
No, yeah, I'm a meaner.
From all of us, Sagar, we're sorry. Very sorry.
I won't do it again, I promise.
Yes, you will.
Neil,
don't make promises you can't keep, Mark.
Sorry, Noel. I mean, Neil. Neil, do you have anything to add about Lagoon Nebula?
Isn't
the
it
Lagoon or the Helix?
I mean, Helix. See, there you go. I'm jumping through so many screens at the moment.
Are you trying to find your tab, Mark? Is that what you're doing? Looking for your tab?
Totally. I'll go back to Pepsi.
Yeah, stick it to him, Claire.
All the way. She keeps me straight.
I don't really have a lot to add to this one. I've attempted a photo of this one before, and I really didn't do very well at it. I'm putting it on my list to reshoot sometime in the future. Planetary nebulae are kind of difficult to shoot. They're fairly faint, and they're usually quite small. The Helix Nebula and the Dumbbell Nebula, which are the two we chose for our vote tonight, are exceptions to that because they're quite a bit bigger because they're fairly close. But I've found them to be challenging objects, and I'm looking forward to having a go again at getting an image that I'm happy with sometime soon. So, sorry, I haven't really got much to add to that discussion, but I think Claire has described it beautifully.
I can just add something if you like, Neil. I'll say that if
Please.
you can zoom in really, really close, what's really cool about the Helix Nebula and also the Dumbbell Nebula is that there's these sort of clumps of material that look, they're sort of heading away from the center, and they look a bit like comets because they've got this clump and they've got these tails of material. So lots of interesting astrophysics still going on. You can't really, I don't think you'll see it here, but there's certainly some beautiful pictures. They're called cometary knots. So there's a little thing for people to go away and do a little bit of homework. There's about 40,000 of them. 40,000 of them.
Cometary knots.
Yeah, cometary
knots.
They
show up very clearly in the Hubble images of this object, but that'd be a bit cruel to Noel to compare his photo to Hubble's.
Oh no, Noel's doing a great job. It's beautiful. I was just, talking about the physics.
Yes.
Now, Noel, I need to ask you. So we've got 8 minutes and 30 seconds. You want to tell us a little bit about what you're using equipment-wise? Because we haven't spoken about equipment tonight at all. All we've been saying is 8 frames stacked, 4 ignored, and 8 minutes and 30 seconds worth of exposures. But we haven't told anyone what you're using, what anyone's using equipment-wise.
All right. Well, I'll work backwards. Normally I work forwards, but I'll work backwards tonight. So what you're looking here is a crop of a my screen, which is using SharpCap, and I'll just go back to the full version. So this is SharpCap Pro, which I'm using to do the image capture. So this is capturing images from my camera, and this is stacking them live. So every image that comes in is being, I guess, mathematically added to one another to filter out noise. But back to the equipment side of things. So this is running on a Windows PC, and that's hooked up to my telescope. And that is this guy here. So for tonight, I'm using an 8-inch or 200mm Newtonian reflector, which is on my EQ6 EQ6 Pro equatorial mount. And I've got a ZWO ASI 533 cooled color camera hanging off of that. I'm using a trying to think what the filter is that I've got on tonight. It's just an infrared block because this camera, stars give off a lot of infrared, and this camera will pick that up well, but it will bloat. They look like fat stars, so I use a infrared block filter on that. And then on top of the scope for wider shots, I'm trying a DSLR camera with a 500mm lens on that, just riding on piggyback. So that's what I'm using tonight.
We jump back to your image you've got there. Yeah. So how many images have we got? So we had 8.5 minutes before. We must have more now.
It's just enough. Yeah, I'm taking 1 minute exposures on this one, so they're coming through slowly because it's
okay, yeah,
kind of funny.
It's pretty good that we've taken 8 minutes and you can see so much detail in it still.
Yeah.
Now, I think what we might do is check that poll for the next one. Oh, it's close. It's close. Oh. Do I call it? Are we ready? I know we weren't. Apparently, we were meant to do planets last, but it was on the list in that order, so I jumped to it. Are we ready for planets? Shall we leave the poll running and go to the next one, or?
I can't do planets until the end.
Okay, let's leave the planets. We will leave that poll open. I'm going to get the next poll going.
I've got Helix up.
Oh, you've got Helix. Oh, you'll have to share your screen again. I'm really keen to see your Helix because Neil, I don't think... you have seen Anne-Marie's images when she does her stacks. They're absolutely amazing. Sorry, everyone else.
Anne-Marie produces incredible work. I admire everything I've seen of hers.
Yeah. So this is 3 minutes coming through. It's so crisp and so clear. So while we wait for that to start stacking, I'm going to get the next one going. And we're going to come back to Saturn versus Jupiter at the end. So it still has time to change. But it's very tight. I will say that. There's a couple of votes between it, which is not a lot. So the next round then that we have is Cat's Paw Nebula versus Eagle Nebula. And that is round 9, fight. And that poll is active. I'm going to leave the other poll going. And this is 4 stacks, Anne-Marie. How long are your stacks?
These are only 60 seconds.
So this is 4 minutes worth of...
4 minutes, yep.
4 minutes.
I was shooting it last night, and 4-minute exposures were a lot better than 4 60-second exposures.
Now, you've been battling cloud tonight, so this is the first
no,
time.
No, it's not cloud. I've just been technical difficulties.
Yeah. I think we've all had those tonight. We had some YouTube technical difficulties. I've had some Facebook technical difficulties. Claire's had some microphone muting technical difficulties.
I don't think she has.
You're just not going to let that lie, are you, Mark?
No,
She managed to unmute that
because
time.
I've made lots of mistakes as well, so everybody else has too.
She's ready with her finger on the trigger every time Mark opens his mouth at the moment.
There you go. Now, we'll let that vote keep rolling along. Oh, that one's close too. Wow. You guys are really giving these... This is... So it's like when you're playing a game of Street Fighter and everyone's just got that tiny... Each player's got the tiniest little bit of energy left. That's what's happening at the moment between Cat's Paw and Eagle Nebula. It is closer than Saturn and Jupiter. That's for sure. In fact, there is one vote between them, between Cat's Paw and Eagle Nebula. So if you haven't
Come on, all you
yet,
cat lovers out there, paws up.
Yeah,
You know
go
what?
Cat's Paw. We always do the Eagle.
No, Eagle's better.
oh, look at this infighting in the live stream team.
At least when I type in, NGC 6334, I don't get a whole bunch of M16 rifles. So there's that.
That's true. That's true. Lee's joined the party with Helix Nebula now.
Well, I couldn't find it earlier. For some reason, slewing in as soon as I slew in Stellarium and then do a plate solve, it was putting me all the way up here. So, I mean, plate solves okay, but just not too sure why it thinks it's.
You've got 2 60-second exposures.
Yep.
Okay,
I'm going to go and check that vote again.
I'm also going to say, Mark, that Kevin has suggested that you could have followed the previous one with a vote for Saturn Nebula versus Ghost of Jupiter Nebula.
Ghost of Jupiter is not. I don't think it's not visible at the moment.
But we could at least put a picture up and have a look at it.
Though.
Yeah,
it's a good one to go head to head. Both planetary nebulae that actually look like planets.
I think we might need to do this battle again when we've got Saturn Nebula and Ghost of Jupiter Nebula up, and do it with some other objects as well. Because you're right. I will say straight up that I would vote for Ghost of Jupiter.
We know, Mark.
What's that?
We know. Just about every stream you say that's your favourite.
Because it is. It is. It's a beautiful object. It really is. I remember seeing it for the first time, Neil, and seeing the colour and being amazed by it, and also being confused at how they thought it was Jupiter, because the colour was it's so different to Jupiter. Now I'm going to end this next poll. Cat's Paw versus Eagle Nebula. Results are in, and it is Eagle Nebula with the win by four votes, I think it was. Not much.
What percentage is the difference?
58% to 42.
Oh,
that's within error.
We're saying that there's enough error there to give Cat's Paw the win. Is that what we're saying?
No. We have to respect the vote of the people, even if they know not what they do.
All right. Well, the guys are going to slew across to Eagle Nebula, and I'll get the next poll going. The next poll is, I might need some help, guys, to explain. So we're looking at NGC 6744 and NGC 300. So can we give the viewers a little bit of an idea of what each of these are? I'll revert to Neil and Claire for that.
I'll get the NGC 300, Claire.
Just a little bit of information.
Sounds good. Give it a bell.
The Gaxelles.
Yeah, they are Gaxelles. For those who can't speak baby, that's Galaxy. NGC 300. And I'm reading from the Wikipedia page here, so I'm not claiming to be able to pull this up from my memory. It's a spiral galaxy and is one of the closest galaxies to the local group. So it's just outside our own local group of galaxies, of which the Milky Way, of course, is a member, along with Triangulum and Andromeda. So it's relatively close, but not in that group. What was that? Sorry, Mike?
That's all we need. Don't give too much, because you're going to have to talk about it when we image it. If you tell them everything now, you'll have nothing left to talk about.
Well, all right.
This is
I'll
just
give
so
a
that we
little
know
bit of
what-
description of what it is.
Yes,
being
that'll do.
a spiral galaxy that is angled at about 45 degrees on. So you're seeing it as a slight oval shape.
And
Okay, and in the red corner, we have NGC 6744. Now, what's cool about this galaxy is it is also a spiral galaxy. It's about 30 million light years away, and it's a little bit bigger, well, quite a bit bigger than the Milky Way. So it's about 175,000 light years across, whereas that's about 100,000 for the Milky Way. But it's actually thought to be probably the most similar galaxy to our own Milky Way. And of course, we'll never really get to see our own Milky Way. Well, I personally won't until we sort of invent intergalactic travel. So this is potentially like looking into a mirror.
Okay, yeah, that's cool, Claire. But this galaxy is only 6 million light years away, and it has some beautiful hydrogen alpha nebulae in its arms, indicating the presence of active galactic or active star formation. So I reckon people should vote for 300.
Well,
This is like
that's fine.
this is like the press conference before the fight, because we're not even up to that fight yet.
I know.
I'll rip him limb from limb.
Has our team got anyone started stacking? Oh, I can't remember what were cats. Eagle Nebula. That was it.
Eagle Nebula.
I've got it. Yeah, I've got it now.
There we go. Oh, it
hang on.
went green.
Yeah, sorry. I haven't stretched yet. I've got to drop the single. There you go.
Oh, look at that.
Now it's
That's
right up.
gorgeous. You can see those structures in the center there, which are commonly known as the pillars of creation. They're absolutely beautiful. And one of the most famous Hubble images is of that region. It's appeared in many different formats in media. If you're a sci-fi TV fan, Babylon 5 used it in the background of one of the battle scenes in that series. I'm sure Claire will be able to tell us a lot more about the scientific side of that. But as a photographer, I just see that as I also see that as a striking feature of interest that really makes the image draw the eye, makes you draw your eye into the center of that nebula there. And Noel's done a great job with only 2 minutes of exposure here.
No, that's
mine.
Lee.
Oh, sorry, my apologies. And Lee has done a great job with just a couple of minutes.
Neil, Noel, Lee. I mean, geez.
Yeah, I'm going to mark that one down either way. It's a Neol.
A Neely. You nearly got it.
Nearly there.
Oh God, I think I'm ready to be a dad. I just want to point out to Denise.
Yes,
Denise has brilliantly brought in a reference to Monty Python, probably one of my favorite movies. So thank you, Denise, for referencing the Black Knight. Rip your bloody arms off. That's the worst English accent ever. Yep. Anyway, I watched that the other week, Denise. So thank you very much. Not for the first time. Probably for the 105th, not counting or anything. But what's really great here is so what Neil was talking about in Lee's image is these sort of dust pillars. These they're called the pillars of the creation, and they're actually only a tiny part of the Eagle Nebula, but they're really beautiful, and they're another type of sort of stellar nursery sort of thing. They span so the Eagle Nebula is about 70 by 55 light years, so it's a really big area. But these pillars of creation are actually active star-forming regions. So we've actually had a few of those tonight, which is why I think we should probably head to NG633 for after this, not Neil's preference for the star-forming regions. I'm just saying. Mine has star-forming regions too in the outer areas, which is really cool. But anyway, so these pillars of creation are basically really dense, dusty, cold areas where we've got stars forming, and you can't actually see them inside the dusty nurseries. So eventually, when they all ignite, they will blast this dust and gas away.
Now we've got a very good comment by David Unwin. NASA has turned this image into a sound image. Have any of you guys heard it? Have you listened to it?
I'm not sure I know what a sound image is.
So they've taken the image, I believe, and turned it into sound. They did something similar like this with Saturn, with its rings. They turned it into
You're
sound.
referring to the radio frequencies that are detected from this and turning them into audio frequencies.
Yes.
Yeah.
Not always
Fascinating. I
radio.
didn't know this was a radio.
It's often called sonification. So you can turn. I think actually Katie O'Connell talked about this in your just before your general meeting the other day, and it's called sonification. So you can actually convert data into essentially a scale. Any data on a scale, you can essentially convert to sort of an audio scale in pitch, and you can sort of make a sound representation of that data. And so there's lots of things that have been sonified, I suppose. And I've actually just got it here, but I doubt that I can share it. So,
You can try
I'm just
if
not
you
in a sharing
want.
mood.
No?
I can try.
See how you go. See if you can.
Well, let me see. Let somebody else, do some chatting.
I've actually
see if I can
got a question for Lee, which was
Yes.
inspired by a comment in the chat. Lee, what is that glow that appears to be coming from the right-hand side of the image? Is there a bright star just out of the frame?
No, that's amp glow on my camera. So if I, because I am, excuse me, I'm stretching the image. If I take that stretched image off, you don't see it, but you can just see things there. So we're stretching the image to make it, more visible. But because I'm also taking this with a fair bit of gain up here, it's effectively noise from the camera itself, and a lot of cameras have a amp glow that you'll basically see in most of them. And this when it's stacking here, it doesn't include any bias frames, which would normally get rid of that. So if I were to stack this later on, where am I going? So if I was to stack this later on, I would use some bias frames, which will actually remove that noise that's there.
Astrophotography cameras, especially this kind of design, are very sensitive to near-infrared light. And infrared, of course, is heat. So when you have a chip right next to the sensor that's doing a lot of work, it heats up a little bit. And sometimes that heat, the infrared from that heat, can spill over into the side of the imaging chip, the imaging sensor, and appear as a bit of a glow. So that is an artifact of the design of CMOS cameras, which are the modern digital SLR type designs. CCD cameras, which is more the scientific instruments, their amplifiers are next to every single pixel site. So every single photoreceptor has a tiny little amplifier next to it. And so they don't experience this amp glow because there's not one single amplifier outside the chip that is doing all the work.
Now, I'm going to digress a bit. I've seen in the chat that there's been a link to YouTube, and I've also been sent the link to the sonified Eagle Nebula pillars. So I'm going to try and share this and see if we can play it. See how we go.
It's quite eerie, actually. Yeah.
I have heard another one. I don't know if it was the
Give it a go. Give it a go. Bear with me. I've got to get it going in a different tab.
Just while we're waiting, Lee, I have a request from me and from chat. Can you just click on the auto color balance in the because the green is getting on my nerves.
Sorry, I didn't redo it after I took the stretch off before.
It was looking pretty green there for a while. Maybe
it was offending my photography sensibilities.
Oh, I just thought it had been on a roller coaster for too long. Okay, now let's see if we can get this to play. See how we go.
Oh, there's that beautiful NASA shot. It would help to unmute it.
I have.
I don't think it's playing, is it?
Was it not working?
I can hear it.
What we
Hear
were
something.
looking at on screen, we weren't seeing. We were only seeing it paused and muted. And have we just lost Mark?
Well, that would be strange.
Yes, it looks like we have.
Wow. Okay,
That
so
was
the cat's away. Let's play, mice.
I'm
Oh,
back.
no.
My gosh. Oh,
Do you want me to
welcome back.
try? I'm not sure if I can share.
Yeah, can you
Going to
try and
get
share?
you,
Sorry, I tried to share and it did not work. But I tell you what, it does sound really good. I can tell you that much.
Mark, try unmuting your mic.
Can you see?
I was unmuted. Yes, I was absolutely
see?
unmuted. I think the problem was I was trying to share it while I'm streaming and hosting a stream, so it didn't.
We
like
can
that.
see.
Okay,
Yeah,
let
we
me
can
see if I
see.
can play
Right.
this.
Here we go.
So while I've got you here, I'm going to just show you the link that's been put up, and that was here. NASA actually has sonified a lot of data. So there's the Whirlpool Galaxy, then there's also Cat's Eye, I think, and there's ones that we actually talked about. There's the Dumbbell down here somewhere, Helix Nebula. Actually, it might be the Helix, not the Dumbbell. I'm getting confused. And the center of our Milky Way. So what's really great about sonification is it's just another way to understand data, but also it makes it accessible for people that cannot see the images produced by data. So now I need to unshare. How do I do this? There we go.
There we go.
There's a bit
We're
of
back.
just about 3/4 of the way through that, it was a bit of a lost in space kind of sound.
It's creepy.
There you go. Here, look, the 1950s sci-fi movie makers got the sound right, and they did, didn't they?
That's a good old theremin.
That was cool. It was, Michelle. It was absolutely cool.
There's actually we're going to move on to. I know we're going to move on to one of the planets shortly. At the end of of this stream, but there are a bunch of. There's a moon called Enceladus that actually interacts with Saturn's magnetic field, and they have actually sonified the packets of charged particles that travel in this sort of weird flux tube between Saturn and Enceladus, and it's really creepy. So if you're bored one night, type in Enceladus. It's ENCELADUS, and then sound, and usually a NASA page will probably pop up, and go and have a listen to that, and it is 100% creepy.
Now we've got some more data here from Anne Marie. This is 2 of her images. How long are the exposures on this one, Anne Marie?
They're only 60 seconds, but I've only.
Well, you've just muted yourself again.
Sorry, they're 60-second exposures, but I've only got 2.
That's okay. That's fine.
That's looking amazing for just 2 exposures.
For 2 minutes, that's mind-blowing.
Yeah, they're H alpha, by the way. 2 H alphas.
It's
a really cool
what
target.
Anne-Marie means by that is that
I'm working on at the moment.
filtering.
What was that, Neil?
Sorry, I spoke over you, Anne-Marie. What was that?
That's right. I was just going to say this is what I'm working on at the moment. But I'm taking 4-minute exposures, and they look fantastic.
So what Anne-Marie is doing with this image here, with the technique she's using, is she's imaging through a filter that permits through only the frequencies of hydrogen alpha wavelengths of light, that red color. And the advantage of that is that it cuts out all the other light, so it increases the contrast. It also makes the hydrogen alpha stand out in contrast as opposed to all the other sort of light that's mixed together. So you get more detail and more contrast, which shows up the features better when you're using a narrow bandwidth filter like this hydrogen alpha filter. But it does mean that you need to get more exposures and take more time to make up for the fact that you're losing some of the light that would otherwise be captured.
Now, I think we need to check the votes. I really do. I think we need to check the votes. Who had NGC 300? That was you, Neil?
Well, that was the one I thought was a pretty cool one to choose.
Okay. And Claire had NGC 6744. I think we should have done this from the start, giving you two one each to battle off against each other. But I do have to say that I'm sorry, Neil, you lost this one by a knockout.
Woohoo! I'm a knockout.
It's hard to deny Claire's compelling arguments.
Yeah,
Claire, congratulations. I'm looking forward to seeing your choice.
I
Thank
think
you,
there was an
Neil.
uppercut in there somewhere because it was 70% to 30% towards NGC 6744. So it was quite the result. So if the guys want to start slewing across to NG 66744, I will get.
The funny thing was when Claire yelled out, "I'm a knockout." All I could think of was "It's a knockout,"
It's
and
a
that was
knockout?
another 80s reference anyway.
That's the name of the game.
It's a knockout. That's it. What's the name of the game? Oh, and the guys were when they wore the giant suits, and oh man, bringing back memories. Oof.
Those shows were poor imitations of the Japanese versions, which were absolutely brutal.
Oh yes, I have seen some of those.
If you've never seen it, do yourself a favor after the stream and go to YouTube and do a search for Takeshi's Castle, and be prepared for a lot of wincing and cringing.
I have seen some of Takeshi's Castle. It's a bit crazy. Now, Neil, Claire, one of you has to choose the Witch's Broom Nebula, and the other one has to choose Pickering's Triangle.
I don't know
Neil,
either
as
of
the
them.
loser, you can choose which one you
Alright.
like.
Neil lost it.
Oh, okay. Give me a second. I'll have to look at what they are.
Ooh.
They're both Veil Nebula stuff, aren't they?
Are you talking about the Witch Nebula? The Witch Head Nebula?
No,
No,
Witch's Broom.
There's a search for
Broom
Witch's
Nebula.
Brew doesn't bring up anything except for the Witch's Head.
Broom.
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 I was thinking more like the town of Broom, but anyway, okay.
Not Broom either.
It's all part of the Veil Nebula.
Yeah,
And
it's
what was the other
definitely
one,
Veil.
Mark?
Yeah.
Pickering's
other
Triangle.
one was Pickering's Triangle, and Neil, I will say that Diego is bombarding me with amazing images and telling me I have to show you.
Okay, well, I'm
Showing-
going to
showing
put my efforts behind the Veil. The Witch's Broom Nebula.
Yeah.
This one is absolutely stunning. It's a sheet of nebulosity, both hydrogen and oxygen glowing. That's as a result of a supernova remnant, which is coming up against a bright star that appears to be sitting on top of the wave. And the contrast of the hydrogen, the oxygen, and that Sol star right on top of it is absolutely striking.
All right, now, Claire, can you sell Pickering's Triangle?
No.
No.
It looks beautiful.
It's
It's all gorgeous, to be honest.
Anne-Marie, over to
You can't
you.
pick a loser. Yeah, Anne-Marie, I'm happy for you to fight for me, but you can't pick a loser, I don't think.
It's just got so much colour. It's beautiful. It fills the frame. It's nice.
Oh, there you go. It fills the frame and it's full of colour.
The Witch's Broom's just a
Spoken
little...
like an astrophotographer.
Yeah.
I can't argue with that.
But also Pickering's Triangle is part of a supernova remnant called the Cygnus Loop supernova remnant. I think it's gorgeous. And I reckon it's got probably, I don't know, it's so dense. You're right, Emery. It's got a really dense structure in it, and it sort of almost looks like it's all puffy, like explosion clouds. So, it doesn't, I don't really see why it's a triangle, to be honest, but yeah.
Yeah, it is a triangle.
The other thing to think about on that front, Claire, is our speaker on Wednesday, Katie. She was talking about supernova remnants.
Well, that's good enough reason to go with me, I guess.
Well, the Witch's Broom is also part of a supernova remnant, but I do agree with Claire. I don't think you can pick a loser here. They're both stunning objects.
All right. So on that note, it is Witch's Broom Nebula versus Pickering's Triangle, round 11. Fight.
Personally, I think you should just look at both.
Yes.
No,
Well, we can.
It's not the name of the game.
They're right next to each other.
Yeah, exactly.
Now,
Can't we have a
This was never
participation
an
prize?
option.
Now we've got to go to NGC 6744 and see if any of the guys got NGC 6744 going yet.
Try.
Just doing a
They're
first
trying.
sub to see if I'm there.
All right, we'll watch our black screen here and see if that improves in view.
So to explain the terminology to folks listening tonight, Lee is saying he's waiting to get his first sub. He's not looking for submarines. These are sub-exposures. And the reason it's a sub-exposure is because we use a whole bunch of these to add together to create our final exposure. So a sub-exposure is a whole image by itself, but it is one of many that we'll put together in order to create the final result. So what we see here is a sub of, I think that was 15 seconds, but now we've gone down to just 2 seconds, and I believe that's to assist Lee in centering the object.
Yep, just going to move it over a little bit. Well, wrong way.
Here we go. I'm going to jump over to Noel's because Noel's got it on there already.
Okay, at least now I know what it looks like.
And I'm seeing some beautiful spiral structure in that already.
That's what I'm saying, because for some reason my plate solving is putting them a little bit further across than what they, I believe, should be. So,
while I've got that building up, I'm going to be a bit sneaky and just for Claire's benefit, that's cat's paw that I was stacking earlier in the background.
Oh, beautiful.
It's gorgeous, isn't it?
I don't believe that was on the view. I think that lost the battle. How did that get in there?
I snuck it. It was Claire's request.
Oh.
That's right. I did ask for it. After everything you've said tonight, Mark, I think I deserve this.
I agree.
Thank you.
I would have agreed with Claire on that one and told everyone to go and look at the cat's paw.
It is a beautiful object. It's absolutely beautiful object. So
pretty big cat, really.
Very big.
Have you seen our cat?
Let's make sure it doesn't get anywhere near our solar system, hey? So you can see some shape appearing there.
We've got a 13-kilo Maine Coon, so
that's bigger than a lot of dogs I've seen.
Yeah, that's huge.
That's the sort of cat that gets what it wants when it wants it.
Yep.
And gets others to do it for it.
Absolutely.
Look at that. Andy snuck one in as well. Cheeky bugger.
Oh, since we're all showing our cat's paws, I'm going to put mine on as
well.
No. Yeah, definitely. That's right.
That's two cat's paws more than should have been shown.
I've got a dog paw, but I've got to get him.
Got to bring him into the cabin.
Into the room, and I'll show you his paws.
Into the room.
The tent.
So, who'd like to tell us a little bit about NGC 6744 as we start to stack images?
I can tell you a little bit about it. So I think I have to. I'm sorry about that.
You want it.
So this is like essentially like looking into a mirror. So if there were any aliens living in that galaxy and they looked out at the Milky Way, they potentially could see something quite similar to what we're seeing as we look out. As I said earlier, it's a little bit bigger than the Milky Way, so about 175,000 light years from side to side, which is 75,000 more than ours. However, it's very, very similar because it has a spiral structure and it also has this kind of fluffy outer spiral arm structure, which we think our Milky Way also has. When you look deep into the center, just like the Milky Way, if you look deep into the center of this galaxy, which I'm sure we'll start to see, and you can already see this yellow glow, and that's actually light from old, cooler stars. So these are not the stars that are massive and only last a million years. These are the stars that sort of tick over for a very, very long time. They're steady, they're easy. They're your sort of accountant. They keep working for the rest of their lives and make a good steady income. And they're not these big, bright, flashy Nirvana rock stars who pop off the universe early. So these are the sort of, the accountant version of stars in my little job description. So these are the yellow. They're not boring. They're stable. They're dependable.
They get to work at 9 and they leave at 5.
That's right. And they do everybody else's taxes.
4:55.
They're probably the only kind of stars that could potentially have life around them too.
That's exactly
they
right.
live long enough for life to be able to evolve on planets that orbit them.
That's
Yeah, and
actually
also
a
their
really good
light
point.
is dependable, so they don't tend to have flares. They don't tend to have so there are some stars that are even smaller that last even longer, but they're sort of don't put out a regular amount of light all the time. They sort of have an unstable environment, so they have little bursts of activity, which is not great if you're trying to sort of level up from unicellular to multicellular life form, I suppose. So yeah, you can see the yellow glow in there, and those are lots of very old yellow stars. And if we were looking back at the Milky Way, that's what we would see right in the center as well. And as we start to stack more, you'll see more of the spiral arm structure take shape with all of the dust lanes, just like we have in the Milky Way. What's really interesting is in the ultraviolet, when this galaxy was imaged in the ultraviolet, they actually found that there's star formation happening in the very outer spiral arms, which is something that we weren't really sure whether it was happening. So it's kind of interesting to see that happening in a galaxy that we think is very, very similar to our own galaxy.
I lost my guiding there for a moment, so we've something happened.
Quite a
We
few
all have that
comets.
problem from time to time in our lives.
There's a lot of comets heading towards us by the looks of it there, Lou.
No, duck and cover.
Duck and cover. Now, while we're doing that, I have been sent a really nice 4-hour image version of this by Diego.
This will be good.
Share it. So just bear with me. I'm going to open it up. And he agrees that it is a very difficult object to image as well. So let's get that one going because I know Noel is working on it at the moment as well. So this,
I can hear your brain working overtime every time you say one of our names, mate.
I know. I'm getting there. I've only mixed them up once tonight, so that's a win.
Yes, I'm impressed. Wow,
So
that's a stunning image.
4 hours of the galaxy that we're trying to image, and that you can see the orange that you're talking about there, Claire. That fuzzy orange.
Right.
Yeah,
that's just basically the light of thousands and thousands and thousands of stars right in the center there. I just find that mind-blowing, really. And what's really interesting as well about this galaxy, you can go, Neil.
I was just going to say that I love that you can see a dwarf galaxy as a companion orbiting just above the plane in that that's angle of that shot.
Yes, you can.
Oh,
yeah. Sort of at about 11 o'clock-ish.
Yeah. Which is quite typical. Yeah.
And I can see another one over sort of right out just above 9 as well, further towards the edge on the left-hand side of the image there.
Indeed.
So there's a few, but we're going to go back to the live stack. So this is the live stack version.
It's coming, isn't it?
Yeah, this is Noel's live stack version. This is amazing.
Interestingly enough, this galaxy is potentially, they think that maybe it's actually merged a long time ago, actually merged with another galaxy. So if you're sitting there thinking that it's an unusual thing for galaxies to merge, it actually probably isn't so much, especially in the early universe when things were very close together.
I really enjoy watching these come in these live images, and so this is 3 minutes on this galaxy live as we're watching it. And I just think it's amazing to be able to sit here and, for 3 or 4 minutes and just watch this appear in front of our eyes. Now, while we're stacking it, I'm going to go back to the Witch's Broom Nebula versus Pickering's Triangle. Who had the Witch's Broom?
That was the one
Neil.
I was championing.
Witch's Broom has responded in the battle and thrown its own knockout punch.
Well, it's got a cool name. Come on. Witch's Broom's way cooler than Pickering's Triangle.
And it actually does look like a Witch's Broom. And the end results, I've shared the results now, is that Witch's Broom, 81%, Pickering Triangle, 19%.
Wow.
I would agree with that, guys.
Claire,
I think you've done fine.
I would say that's down to the name.
Yeah.
Yeah, I reckon. Well, no, I mean, you did a really good job at pitching that, Neil. Well done.
Thank you. Just before we do move on to that, though, Mark, and to give our astrophotographers a chance to slew over to that, because we were just discussing the motions and collisions of galaxies, as Claire was describing with this beautiful galaxy, which I'm now, the more I look at, is this Knowles version now, the more I'm seeing in the extended arms of this galaxy. This is amazing what we're seeing here for only like 5 minutes worth of data collecting. It's
unbelievable,
great work,
isn't
Noel.
it?
Yeah. But what I've found is a video of a simulation of the formation and collision of galaxies. So when we're talking about the galaxies colliding, like for example the Milky Way and Andromeda are going to get together and eventually merge, you might think of that as two discrete objects in space that get near each other and then blend together. But it doesn't work like that at all. Space isn't quite so discrete. There's lots of material that is all around the galaxies, all around and between them. They're just not dense enough to be clearly visible when you take photos of the night sky. This simulation, however, shows you a bit more about how messy and how complex these interactions can be. So you can see there's a sort of a large spiral galaxy in the center there, and a couple of maybe dwarf irregular galaxies out to the right there now. But there's no real distinct border between them. You couldn't draw a line across and say, here's where one ends and the other begins. And that's what it looks like when they sort of come together. They fling around each other, they disturb each other, create waves and ripples and distortions in the shape, and eventually they'll settle down into something that's a little bit more like we'd expect to see when we're looking at a spiral galaxy. But it's definitely not a discrete event. It's not a clean merging. It's a real turmoil and maelstrom going on in these structures.
It's a beautiful thing to watch.
Oh, I could watch this sort of stuff all day.
It's also very destructive, but
oh, here comes another one about to merge. Look at that. Oh, they stopped it right at the crucial moment.
It's quite interesting there as well, because that's quite early in the universe. So it was 4.28 billion years ago, so into the life of the universe, which was quite early compared to now.
Yeah.
So the galaxies are a lot closer together generally. No, that's okay. No. So the filaments that you're talking about that actually connect galaxies, I mean, we see this structure on a much, much larger scale when we start looking at superclusters of galaxies, and then we get out and have a look at the sort of the galaxy, the scale of the whole universe. We see this sort of void and filament structure where things are always connected. So it's kind of interesting that as we get smaller and smaller and smaller, we still see that. And then as we get further and further out and we look at the structure of the universe, we see the same sort of idea where there's bridges between hubs, I suppose, but also the different types of mergers. There's types of mergers called wet and dry mergers. Wet galaxy mergers are when two galaxies come together and there's lots of gas. So that's typically when stuff's flying together and stuff's actually merging. Dry, and that typically happens with spirals, and it usually sparks a whole bunch of new stars, so some new stellar nurseries, and you get explosions and star formation. Whereas for gas poor galaxies, which are things like ellipticals typically, because they're old and all the gas has been blown away, you don't necessarily get that same sort of, like, I suppose, physical touching kind of merging. It's sort of dry merger because there's less gas, and you don't tend to get as much of sort of star formation because there's just not so much gas around. And a lot of the time galaxies won't actually necessarily merge. They might do what Neil said, and that is like come past each other and gravitationally affect each other. So we get starbursts, and then they might actually just continue on their merry way. And then other times they do definitely sort of merge, but it's not necessarily a physical merging of pieces of material. It can actually just be stars become incorporated within that sort of bigger new conglomeration. But what's really interesting as well is when two supermassive black holes get so close that they merge. And then you do definitely get some really crazy stuff happening, like ripples in space-time itself, which is just so cool.
Now, we were talking before in that image that we popped up of Diego's about the little fuzzy galaxy off to the side. I can actually see it in Noel's image, right at the bottom of the image there.
Yes, center, bottom center.
Yes, bottom center. You can just make out that little faint fuzzy that we were talking about before. That's it there. Yep, right there. So, and how many minutes of image is this now, Noel? This is 9 minutes.
About 9 minutes, yeah.
Yeah, 9 minutes. Wow. 9 minutes, and you're able to pick up that little faint galaxy sitting there at the bottom there.
Yeah, I have to congratulate Noel in this shot. I think it's just a remarkable, breathtaking result for such a short time that we can pick up that distinct structure. We can see those arms. We can see quite a broad distance across the disk of this galaxy. It's also very clearly, you can see the bar in the middle that are connecting the arms.
It's quite amazing for 9 minutes of live imaging to be able to see this much detail.
And Claire, remind us, how far away did you say this object was?
I think it's about 30 million light years. Yeah, 30 million light years away in the constellation Pavo, the Peacock.
Pavo.
30 million.
Yeah, 30 million light years away.
A light year is around about 10 trillion kilometers. So 10 million kilometers. And this is 30 million of those. So it is a very, very, very long way away. And yet we can still get an image of it like this, which is just breathtaking.
I love how we talk about distances in light time travel, really. Because, light is sort of, for us, it feels instantaneous. You switch on a light in your kitchen and it's there, and the fact that those photons, those pieces of light, have come from something that's emitted it, and it's traveled through space for 30 million years just to go down the barrel of a scope and hit a detector. I find that absolutely mind-blowing. That my brain has no way to process that sort of distance. Yeah, so it's just one of those awe-inspiring things, really.
I agree completely. It's one of the stories I love to tell when I'm doing outreach with the public. I tell them about the journey of the photon that they are either seeing captured on my camera and displayed on the screen, or they're looking at through a telescope. When the photon is first formed, it's in the center of a star, and it takes tens of thousands or millions of years to get to the surface of the star. And then from that, it takes hundreds, thousands, millions of years to travel the distance between that star and the telescope. It bounces off a couple of pieces of glass, gets reflected by another piece of glass in the eyepiece, then flies into your eyeball, and it finally ends its journey where it hits a cell in the back of your eye. And that then gets converted into a little charge of electricity that flies up a nerve cell into your brain, and your brain then makes sense of that by turning it into an image. And that whole process has taken as long as the dinosaurs existed to happen. And you're able to experience that personally in the backyard with a cheap piece of equipment on any clear night. And it just blows my mind.
So here's another one for you, for the two of you, actually. So we're saying, was it 30 trillion light years away? Is that what we were saying?
30 million light years away.
30 million light years away.
Yeah.
So if we're seeing this now, where do you think the arms that we're looking at right now will be in 30 million years when somebody looks at it again? Because they're clearly not going to be in the same spot that they are right now that we're looking at. They're going to be rotated further around.
Yeah, so this is really a cool question. Yeah, go, Neil, go.
So I think there's a slight delay on my end, and we end up speaking at the same time, and I'm not meaning to cut you off.
No. I waited till you started speaking, and then I deliberately tried to cut in. So you go. I'm joking. I didn't really do that.
What I was going to say is that if I remember correctly, it takes around about 250 million years for our Milky Way galaxy's arms to complete one rotation. And just to be clear on that, that's not the stars moving around, because the stars, while they do move, the structure of the spiral arms is a wave formation passing through the galaxy rather than the movement of the stars. So the rotation of that wave in our galaxy, if I remember correctly, Claire, please correct me if I'm wrong, is around about 250 million years, 250 million years. So if this galaxy, it's larger, so that may be slower, but if it's similar, then in that time it took the light to get here, it's probably made maybe a quarter of a rotation.
Oh, I like your order of magnitude estimates. That's great, Neil. Really good skill to have. You've done it twice in the last 5 minutes. I'm very impressed. So you're right. Basically, there's two types of the stars themselves actually do go around because the supermassive black hole in the center, and then actually sort of takes all of the material in the galaxy around and around and around, sort of like a solar system sort of thing. But you're absolutely right. There are two types of things going around. You've got what's called a density wave, and it's a really strange thing to think about. So you've got these stars going around, and then you've also got these density waves. And the density waves are what, as Neil said, what causes the spiral arms, and they definitely go at a very different pace to what the stars travel at. And so we sort of see these clustering of arms as they go around. And so you're absolutely right. All I was going to add to that really when I tried to cut you off was that this is sort of going back to what we were talking about before with Doppler effect and Doppler shift and so redshift and blue shift. When galaxies are completely face on, so that we are looking at them basically 90 degrees to our own orientation. So if we can see a spiral arms exactly face like it's a pancake flat on our image, we're looking at it 90 degrees to our own orientation sort of thing. We can't really get any redshift or blue shift because it has to be coming towards or away from us in order to have redshift or blue shift. So when it's just going around in the same position, essentially down and up from our perspective, we don't actually get blue or red shift. And it's very hard to actually get some idea, because it takes so long, as Neil said, for the arms and for the stars to move, to get any idea of how fast it's rotating, I suppose, from Doppler effect. So when it's edge on, a bit more like the Sombrero galaxy, we can actually look at one side of the galaxy, the spectrum from that. So as I said before, that's wavelength versus flux. We look at one side and we look at if that's blue or red shifted from the light that we expect to see. And we look at the other side of the galaxy and see if it's blue or red shifted. It'll be red if the other side was blue. And then we actually get what's called a galaxy rotation curve, and we can estimate how much all the material is all the way in from the outside to the middle. We can estimate and measure how fast all of those things are actually rotating around that central body. And that's actually, in fact, how we sort of worked out that there's these galaxy halos full of dark matter, because there doesn't actually look like there's enough material from what we can see for these galaxy rotation curves to actually mathematically work out. And so we sort of deduced that there's an extra large amount of material that kind of envelops the entire galaxy in what we call a halo, dark matter halo.
Now, you were talking before about rotations. The two of you were talking before about rotations, actually. Wave rotation? Yes?
Yes. So a density wave. It's
a wave
called a density wave. Basically of density. So, okay, if I have a bed sheet, okay, and for once somebody's helping me make the bed, right? And
Does that ever happen?
Oh, absolutely. Actually, I definitely get. No, really. Like, my boyfriend is actually really wonderful with housework. I just want to say that. I was just making a very,
generic,
very stereotypical joke, guys. Anyway, so if I'm holding a bed sheet and he happens to be standing there holding the other side, and I flick it, the actual particles don't travel along the sheet at all. But the wave, the energy goes through the sheet. And if I've done it well enough, it will actually fly out of his hand and make him very angry. So that is as a type of wave energy propagation that doesn't involve particles themselves moving. So you can think about that as a kind of as wave propagation. We get it in the ocean as well. When you get when you turn around and you get a wave smack in the face because you weren't really concentrating, those water particles haven't actually really gone anywhere. They've actually just been going up and down and rolling a little bit, depending on the type of wave, but they sort of stay where they are generally when the wave passes through. So we actually already experience wave energy without particle displacement or movement from position all the time. So the waves going through these density waves are actually basically like flicking a sheet. It's all those things that bunch up and then they move on. It's more like sound, really.
Another good analogy might be tossing a rock into a pond, and the waves propagating out from that landing on the rock, and the leaves on top of the pond are just bouncing up and down as the wave passes underneath them.
We've we've got a follow-up to that. So why the brightness of the waves?
Okay, so here's the thing. New stars are generally formed in spiral arms. And I have to say that actually density wave theory has been around probably from the mid-1960s, but we still don't really 100% get it all. But essentially, when it's like sound, right? We have compression waves. So sound is a bit not like water at all. Sound is actually more like the particles move in the same direction as the energy. So if I make a sound here, what I'm doing is I'm vibrating the air molecules, and the air molecules are going backwards and forwards, but in the direction of the sound energy. So if I'm talking to you and you're in front of my face, the particles of air are hitting each other. They're not going anywhere really. They're just hitting the next particle. The next particle hits the next particle, but that's in the same direction as what we say the wave propagation, or the direction of the wave. So it's more like a sound wave. And that's what this density wave is. And if you remember earlier, I talked about when particles bunch up, they get attracted to each other. So gases and particles get close to each other, and then they start to gravitationally contract, and you get star formation. And so you get these spiral arms of stars because of the density wave that's just traveled through and pushed everything together, and everything collapses and makes these big trails of stars.
Mark, I've got a demonstration on a YouTube video that you might want to put on screen for a second, which helps demonstrate that wave thing.
Oh, David, I've seen people fly around a stadium in a Mexican
people don't fly around the stadium in a Mexican wave. But I'm with you, Paul. I've seen people fly around the stadium.
Wait, that's crowd surfing, isn't it? That's something different.
Well, yeah, we could call it crowd surfing, or maybe they didn't want to get thrown in the air. Each to their own. Now, while we show Neil's little... here we go. Yep. So a follow-up. Robert's on fire here. Do you mean, therefore, that it's actually an energy wave?
We call it a compression wave. So the wave is being propagated through compression, just like sound. Sound is actually a physical movement wave, and the energy is propagated in the wave. And so it's a density wave. It's a bang, 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 bang. Things get closer together for a moment in time, and then they back away apart again, and then they end up at their mean position. So the energy itself is propagated through the wave, and the wave is a type of compression wave.
So you can see in the demonstration of the video here, the different circles representing sort of the structure, they get closer together and further apart, but they don't necessarily move with it. If I just rewind a bit so we can see that again, that's a bit further back. Keep going.
You're dealing with internet.
Yeah, when we see this here, these are getting closer together and then getting further apart. But any point on that ring is not necessarily going around or backwards. It's just going in and out. And so when the ones going in meet the ones going out, it becomes more dense, and you can see that spiral structure forming as a result. And what was that comment, Mark? Sorry?
You seem to be having some internet issues tonight. You're a bit delayed.
I'm in Cockatoo, so we have rather limited internet access here. So I'm afraid that's the best I can do.
No, that's all right. That's all right. I just wanted to let everybody know that you weren't like that. There was a specific reason for it. That's all.
Yeah, I'm not deliberately trying to cut people off.
I am.
Now, I have to say, as much as we wanted to go Witch's Head, Broom Nebula, Anne-Marie, who was going to be able to bring us some amazing images that is dealing with clouds. So we're not going to be able to do that one, unfortunately. So we're going to have to jump to the planets.
Well, just before you do that, Mark, I can show folks a beautiful photo from NASA of that.
Oh, yeah, if you could. And then maybe you guys could talk to it. And while you're digging that up, Gunnar wants to ask a question. Is that a process where star formation happens when we're talking about the spirals of the galaxy?
Yes, absolutely it is.
Yeah, 100%.
100%. There we
because
go. Nice
things are getting disturbed. Answer. When things are disturbed, they have uneven distribution, and the thicker parts of the distribution end up becoming more attracted to each other. Therefore, they get greater density, they have more mass, they attract more material, and so forth. We start that cycle of star formation. So that's why you'll often see clusters of young stars forming at the leading edge of these compression waves.
Now,
And then older yellow stars in the wake, right?
As they get older, yes.
And become accountants.
That's right. Good old reliable stars.
this is the Witch's Broom Nebula.
And I'm guessing that star is meant to be the witch riding the broom.
Could well be. It could well be. And would you like to talk a little bit about the Witch's Broom Nebula? And before you do, David, universe cats do indeed surf the galaxy waves.
So just briefly, I'm not an expert on this object by any stretch, but just looking at it, I can say what I see, and it's clearly a pressure wave moving through an area of gas and dust, likely the result of a supernova explosion. I believe this is part of the Veil supernova remnant. You can see that the stuff at the front is of a different material than the stuff at the back because it's glowing a different color. Now that color is likely a false color image created by using narrowband imaging of the emission of different elements. I'm not sure what color mapping has been used to display these, but usually hydrogen is depicted in red and oxygen is depicted in blue. So if that convention holds in this image, then you can see it's the oxygen which is on the leading edge there, although perhaps Claire, with her knowledge of the actual physics of this, might be able to be a bit more precise than my guesses.
Oops. I was not listening. Can you say it again?
I was just going to ask Claire if you can confirm for me.
Been one
Would
of
it be
those
that oxygen is at the leading edge of this expanding ring rather than the hydrogen, or is it the other way around?
Oh, I'm not sure. I mean, that's a really good question. I'm assuming, again, it's the same as the colors with the red and the blue, like you were talking about before. But yeah, I'm not actually sure about the problem with images like this, and in fact all images, when we look out at gases and nebulae and dust in the universe, you might think that you are seeing something in front of something else, or that you have some idea of the 3D structure of something you're looking at. But in most cases, it's actually just our brain putting it together for us, and it is not actually necessarily one thing in front of the other. Sometimes it actually isn't clear from an image, and you do need to go back to the spectra and work out what's what. I'm not sure about the shockwave with the leading edge, actually. That's a really, really good question. But yeah,
and that's actually a very good point for you to bring up. I did make an assumption there, and it's important to have assumptions challenged. So that's reminding me to take a broader view of things and make sure that I'm not just saying that this is so just by looking at it, when obviously the universe doesn't always align with our expectations of how it should be.
And there's a couple of people that do a lot with imaging and what they tell us. One of them is Urban Erickson, and the other one is Travis Rector, who's does a lot of photography out of Canada, I think, or maybe Alaska, probably Alaska. But yeah, so they've actually they explore this in depth, and you can actually Urban actually came and gave a talk at a conference I was at, and just judging by, like, basically if you change the color of an image of a particular, I guess, file in an image or a wavelength in an image, you can actually put it to the back and make it look the other way around. And it completely blows your mind, because you think of it one way and then you see the colors change the other way. And it is our normal sort of inclination to assume that if it's darker, it's at the back, it's away from our light source, which is, near us. And so we tend to think of things that are bright and light as closer. It's not always the case, and sometimes it's just a matter of what filter has been colored certain things when you put it all together in an image. And so you're right, it's absolutely important to keep in mind.
Our primate brains evolved to survive on the savannas of Africa and not to understand the depths and scales of the cosmos. So we are trying to make do with inadequate tools.
See, even that could be challenged where we evolved. But yes, absolutely, you're 100% right. We are what we are. We have what we have.
Neil, my brain didn't evolve to survive anywhere.
Oh, we know that, Mark. It's okay.
Mark is a living throwback.
I'm not that bad.
Now he's defending
You're the
himself.
one who brought it up.
That's hurtful. On that note, while you're being so mean to me,
Hey, you're the one who said it first.
I'm allowed to say it.
You picked on me just because I can find my unmute button now. Gosh.
Firstly, I want to thank Michelle and Christina, who have just recently donated some stars to us. Thank you very much for that. Greatly appreciated. And secondly, I need to give us the results because, and I apologise for us not being able to bring live images of the Witch's Broom Nebula, but it's been a very techie night tonight. A lot of tech issues going on around here, and I am actually blaming New South Wales lockdown. They're stealing all of our bandwidth. That's what's happening. The results of the Saturn-Jupiter. This was the closest one of the night.
Wow.
And there was 2% in it. 2%.
Wow.
That is it.
You've got a
And
I got to
choice.
admit, I personally would find it hard to pick between the two of them. Jupiter's
All right,
my
so
favourite,
what-
but Saturn's such a crowd pleaser.
What would you pick if you had to guess what the result came in, Neil? Which one would you have said got the 2% above the other?
Oh, look, it's because there's only 2% in it. It's just got to be speculation. If it was a bigger margin, I'd say it's likely Saturn would have won because Saturn is such a very popular crowd favourite. But we're not necessarily dealing with a typical public audience here. We've got a lot of very educated, very aware people who love astronomy watching this show, and so they maybe have a greater understanding of how great Jupiter truly is.
So what you've got to pick one. You can't sit on the fence.
I'll pick Saturn. I'll pick
I'm on
Saturn.
Saturn.
Yeah, you're both
Saturn
wrong.
for the win.
You're both
Jupiter.
wrong.
Hey!
Jupiter wins by 2%.
I'm glad because I prefer
Oh, this is
Jupiter.
rigged.
It's rigged.
Oh, look at that for the jump.
It's rigged.
It's absolutely rigged. Yeah, I created 40 Facebook accounts and went in and voted. No, I didn't. I got better things to do than that. So on that note, we will. I was going to jump to Anne-Marie's because she's been struggling all night with tech issues, and it's kind of there. We'll start with Anne-Marie's kind of their image of Jupiter. Anne-Marie's been dealing with technical issues. She's been dealing with clouds, as you can see, because Jupiter's disappearing. She's been dealing with all sorts of problems tonight.
Bad
It's been
night.
a bit frustrating for her.
Oh, there we go.
That's
It's
a
coming
pretty
through
good
now.
image of Jupiter. Oh, it's jumped behind the cloud again. I'm going to give you some time to go and get the fans out and blow the cloud away. And
Yeah.
I'm going to jump over to Andy's of Jupiter. So this is Andy's live stream of Jupiter tonight.
Okay. So what I'm going to do, that's just Jupiter there, but I'll knock the gain up because this is quite interesting. But if I just push the gain right up, you can see all the four moons all in a big row on the side, which is quite interesting. But to be a really good visual one to look at to see Jupiter like that. But you can't look at moons and Jupiter in one hit, so you've got to make a choice. So I'll go back to Jupiter. Yeah, beautiful looking at it like that.
Now, Neil, Claire, would either of you like to have a bit of a chat about Jupiter?
Well, Jupiter is my favourite. It's a stunning planet to look at. Anyone with a small-sized telescope can see the moons, can see the bands on Jupiter. If you've got good timing, you can probably see the Great Red Spot, which doesn't look like it's on the side of Jupiter that we can see tonight. But that doesn't matter because even the clouds are gorgeous. Jupiter is amazing in so many ways. It weighs more than all of the other planets put together. It has the most moons of any planet in our solar system. It is the solar system's vacuum cleaner. It has a tendency to suck up comets as they pass nearby. And there's a very good chance that if Jupiter did not exist, then life on Earth would never have had the chance to get off the ground because the increased amount of junk left over from the formation of the solar system would have resulted in bombardments from space
So
for a much longer period than would have been the case if Jupiter wasn't out there.
Neil, I got to jump in there. We actually have a question. Could we have evolved this long without a Jupiter?
And I think I may have given a partial answer to that already.
Yes, so continue on.
It is pure speculation. There's no real way to prove it because we know so little about the early stages of life on Earth. But it is pretty clear that Jupiter has done a tremendous amount of work, if we want to anthropomorphize it, cleaning up the solar system because of its giant mass that attracts and gobbles up comets. I've also been a huge fan of many of the Jupiter observation missions like Galileo and Juno. Some of the images that have returned from those missions have been just absolutely stunning. Saturn has got the beautiful rings. You cannot deny the beauty of those. But Saturn's clouds pale in comparison to the incredible detail and structure that we'll see on the clouds of Jupiter. It's also a planet of extremes. Not only is it the largest and heaviest, but it also has the fastest rotation at only 10 hours. So being a planet that big and having a rotation that fast, that means that the equator is traveling at far higher speeds than the poles, which means that there is a centrifugal force in acting upon Jupiter. And we can see that with our own eyes here when we look at it. That is not a sphere. That is what we call an oblate spheroid. It's basically a rubber ball squished so that the poles are closer to each other than each side of the equator. So the tremendous speeds at which the clouds and the surface of Jupiter is traveling at the equator cause it to be stretched out. Jupiter is just amazing in so many ways, and I love Saturn, but I can't really say that it comes close to Jupiter in my preference.
Now, we have another question. Well, it's more of a statement than anything. No, there's a question in there. So people often ask if Jupiter is a failed star, but if the sun has 99.9% of the mass of the solar system, that means Jupiter would be in the vicinity of 0.08%, making it a long way from being a star. Thoughts?
So when people say Jupiter is a failed star, what they're referring to is the chemistry of Jupiter. So what Jupiter is made of, and that's it's mostly hydrogen and helium, which is sort of the same makeup of the sun. However, you're quite right. Jupiter just doesn't have enough mass to be a star. And what is a star? Well, a star has to, by our definition, have fusion at its core. And the most simple fusion, the easiest fusion, is hydrogen to helium. And the only way that a star can be fusing, the only way that fusion happens with these massive objects is through gravitational pressure. So if you do not have enough mass, you do not have enough gravity to force the hydrogens together to make helium. So you cannot be a star. But they call it a failed star because it's made up of the same stuff. There are also types of, stars, that we call brown dwarfs. They're not strictly stars because they don't fuse hydrogen to helium, but they breathe out energy essentially because they've got so much mass. You've got this gravitational collapse happening, and it's balanced by outwards pressure from the material, so the gas and the dust that's inside the brown dwarf. Now they're smaller than the sun and bigger than Jupiter typically, but they're sort of more what I would think of as a failed star because they just they're sort of shining with their own light, which Jupiter doesn't really do. But they're not actually doing fusion at the core, so they're not a true star, and like the sun, for example. So you're right. People do say Jupiter's a failed star, but it's a bit of a misnomer. They're just really referring to the fact that it has the same chemistry as the sun, but certainly doesn't have anywhere near the mass, as you've pointed out, David, to actually be a star, to do fusion where it counts.
Jupiter would probably have to have between 10 and 20 times its mass in order to get close to initiating fusion. So It's a failed star in metaphorical sense, but it was never really close enough to initiating fusion, as Claire described.
Yeah, and it's kind of lucky as well because had that happened, we've got a star next door to Earth as well that'll be heating us up and also creating a whole bunch of orbital differences that I think would probably make it less conducive to at least life as we know it.
And not to mention, it would be another source of light that for 6 months of the year would be in our nighttime. So we'd only have 6 months of the year where we get night.
Oh, the twin stars, the twin suns of Sulianus and Ram.
We could have our own Tatooine, though.
Oh yes, you've gone for the.
I've got Star Wars.
For Star Wars, I've gone for Hitchhiker's Guide.
You went Hitchhikers, I went Star Wars. It's okay.
For a moment there, Claire, I was wondering if you knew the names of those stars in the Tatooine system and thought, oh, wow, is that some Star Wars lore I haven't heard about?
Sure, Neil, I'm sure you know the name of them.
No, I don't.
Oh, wow.
I didn't know that they had names. Maybe they don't.
Well, they probably do, but I don't know the name of them. I like watching the movies when I watch Star Wars or any of those sort of movies. Switch the brain off. So I don't pay attention to that level of detail.
That's the Marvel movies for me. That's where I switch my brain off.
Oh, you have to, and then they're brilliant. Just quickly, Tamworth Regional Astronomy Club in New South Wales. Thank you for joining in.
Hi, everyone.
Yeah. Sorry you're in lockdown. Welcome to the world of Victoria for a while. It sucks, and we're glad you can join us, and we hope you're enjoying the stream tonight.
Now, hang on, Mark. We're not glad that Tamworth is in lockdown.
We're glad that they can join us.
On the stream, not in lockdown. Okay.
I'm glad that they can join us on the
stream.
Do
you know how the YouTube users were all resetting their browser? Mm-hmm. Is there a way to reset, Mark?
No, it doesn't happen. It doesn't happen. I'm sorry. I'm unresettable.
Give him a keg of beer and he'll pass out at the end of the night.
I didn't realize I was on mute before, but I was trying to say that Tatooine actually had 3 moons. It was Gomarasan, Gomesa, and Shanini.
Oh, there you go. There you go. Oof. 3 moons.
Love some Star Wars lore.
My T-shirt shows 2 moons, so I'll stick with that. Following on from the Jupiter questions we've had with if it wasn't there, would we be here? And all of the meteors and asteroids and comets that it has swallowed up. Robert is asking, is this why there are so many moons?
Yes. So essentially, gravity, if you think about gravity as a well, so the sun sits in space, and the space is like almost like a trampoline with this is a 3D representation, so it's very hard to really imagine in 4D. But if you've got space as your trampoline, your fabric, and you've got something very heavy in the middle, you've got that kind of space is warped, and that's the sun. And then as you get further away, as you can imagine with the trampoline surface, it sort of levels off. And so Jupiter's at a big enough distance that it's kind of far away enough to not sort of the space around Jupiter is perfect because it can kind of sit on the trampoline without rolling in towards the sun. And that means that anything in the vicinity of Jupiter is actually attracted to Jupiter rather than being attracted to the sun. And so that's basically what's right. Basically what Mark just said. It's gone through its life kind of collecting bits and pieces, a bit like my grandma, actually.
It's like most grandmas, isn't it?
I've picked it up, unfortunately. I think it's genetic.
I think you're right. My father collects a lot of stuff that he doesn't need. Hi, Dad. Now, Noel has been working on something in the background. It's Suzanne Marie's Jupiter Through Clouds. I'm not sure if he's got it. He's been trying to find something that's been quite popular, quite popular in the world of astronomy at the moment. But he's not quite got there. I'm going to try and stall to the point that I think that even though we have done Jupiter and Saturn lost because it was so close, I kind of feel like we have to go to Saturn. So I think we've got to jump
reversing your previous policy of letting the losers suffer in loneliness.
Well, we're talking 1% difference, and I'm doing that because Noel is working feverishly in the background to bring us a live image of something that has been quite big in the world of astronomy in the last few days. And if he can get it, it would be great to see a live view of it. So I'm going to try and stall a little bit longer on that one if I can.
I'm never going to argue with seeing Saturn. It's gorgeous as well.
It is absolutely stunning. And as Anne-Marie's just said in the message, can you see how much wind and cloud we have? Yes, that image of Jupiter is bouncing around like...
Wow.
That's a pretty strong wind if you can blow Jupiter around that much.
Yeah. So what you're seeing there is the wind buffeting her dome and her equipment quite dramatically and bouncing it around.
Well, let me help you stall, okay?
Yes.
Something fascinating about Jupiter is that until we sent Juno, a craft that went and visited Jupiter, until we sent Juno to have a look at Jupiter, we actually figured that the magnetic field was going to be very much like Earth's, and that is comes out one end and goes in the other. So most of you might know, we've got a geographical north and a geographical south pole. So the north is what we would see as north on a map, is at the top, but that's actually our south magnetic pole. And in Antarctica, well, close to Antarctica, is in fact our north magnetic pole. And we assumed that Jupiter's poles would be the same. But when Juno got there, it actually measured the magnetic field. And Juno has a totally normal north pole. And it's actually got two south poles. So it's a little bit bizarre and very, very different from what they expected. So two south poles sitting there. And they're sort of like, oh, God, why is this? And we don't really know. Magnetic fields are still especially planetary magnetic fields, it's still a very complicated area for us to model. I mean, the dynamos, even Earth's magnetic field, even the materials that smoosh around, the magnetic materials smoosh around inside our Earth's core that produce our own magnetic field. I used to be a geologist, actually, and I remember learning about these. And you can pull up models of this, what we call a geodynamo, of this nickel and iron and all this stuff in the core just smushing around and producing electrical and magnetic fields. It's so complicated. It's not just like your normal bar magnet picture that we normally draw. So Jupiter's is even more complicated. But at the middle of Jupiter, so Jupiter's actual core, don't actually think, obviously, most people would know it's a gas giant, so it doesn't really have that rocky core that Earth has. And it instead has basically pressurized liquefied helium and hydrogen, and they don't really mix very well. So potentially that could be what's causing these double south poles. And then there's also just sort of this structure on Jupiter where we've got this liquid metallic hydrogen, which is electrically conductive. It's just very unusual, the magnetic field of Jupiter. And it's a real shame for me that we never from Earth really get to see the bottom of Jupiter that Juno got to picture. So if you ever have any time and you're just browsing around the internet, go and pick up some images of the pole of Jupiter, the poles of Jupiter, and you see these beautiful storms that just go around, and they're absolutely gorgeous. They're sort of these amazing geostructures. They're just cool. So there you go.
Cool.
That's a stall.
That is a very good stall. And Adam Joyce, when you're talking about flipping magnets, is like, flipping magnets? How do they work? Or
Miracles.
Is it flipping magnets? How do they work?
So basically, all you need for a magnetic field is you need the line, what we call the field lines. So the field lines they exit one part of the magnet, that's our north pole, and they enter the other part of the magnet, which is our south pole. And that's our typical bar magnet, or even a horseshoe magnet. You see, if you draw the lines, if you do it with iron filings, that you sprinkle over the the horseshoe magnet, you'll see the lines. And they always go out of one pole and into the other pole. And the thing with planets like Earth or even the sun, where they have crazy magnetic fields, when the source that is causing the magnetic field varies in time and position, you can actually get magnetic field lines that weaken, and then if there's more going out one area than coming in the other, essentially that becomes the North Pole. So that's essentially how. It just changes in the geodynamo at the core that will cause the magnetic flips that we see in the rock records. And I think we have a geologist somewhere in our stream. I think Gunnar was saying that he is a geologist. So beautiful sights. I love it. And we see records of the Earth's magnetic field flip, certainly in some of our structures, our volcanic structures underneath the water surface. You just see north, south, north, south. It's absolutely awesome. And we really only discovered that when we did magnetic field tracing along the Earth's ocean beds. Really awesome. But basically the answer is it's a dynamic system. It's not a simple bar magnet that sits there forever looking like it does. It's caused by material moving around inside the Earth's core. And then, you get a certain flip over to the sort of one person more on the seesaw the other side, and it flips. Oh, there's that picture.
There's that picture. Thank you, Neil. We have another question from Robert. Robert's on fire tonight. Can I just say that? Is the core of Jupiter possibly non-homogeneous?
Possibly. So part of what I was saying before about the non-mixing between helium and hydrogen, they actually reckon that potentially down below the, gas surface of Jupiter, deeper down towards the center part where you've got liquid hydrogen, they may actually have helium rain, which definitely suggests that it's not mixed well, which is why you probably get sort of electrical currents being formed in certain areas and not in others, and then moved around when it all gets sloshed around. So I think it's absolutely amazing. And also because it's gaseous, you've got winds and stuff that actually affect all the way down. And so they think that there's conductivities all over the place because you've got this rain, you potentially have this rain, you have winds moving it around to a very low level. So yeah, it's very unknown at the moment. And I guess we can't really just go and have a look.
Pretty cool if we could just go and have a look, wouldn't it?
Yeah, it'd be very brief.
Oh no, we wouldn't last too long, but
we'll send Elon Musk, shall we?
No, he's all right. He's all right. We'll send Jeff Bezos.
Look, they're all okay. They're all doing things, but I'm not sure about.
Musk is doing.
You don't earn $1 million, you take $1 million. Sorry, you don't earn $1 billion, you take $1 billion. So they're doing good things, but they did it on the backs of their employees. So I'm of two thoughts.
Though, isn't it? But also, I'm not so sure about filling the latest thing. The one thing that's got my ire at the moment is that, and that's IRE, not my I. My annoyance is the idea of advertising from space. The idea that you could put someone's slogan across my night sky makes me quite upset. Not to mention all the strings of satellites that are going up. So,
just one point in Elon's defense there, and I don't like Elon, but the media reporting on that story was, as usual, greatly exaggerated. What they're suggesting is, what Elon is suggesting is to put up an LCD screen on one of the satellites with a camera pointing at the LCD screen, and letting companies put their images on that LCD screen for the camera to photograph with the Earth in the background. So it's not intended to be a billboard that can be seen from the ground.
Not better.
But I wouldn't put it past Elon if he could.
Yeah, I wouldn't put it past. Maybe that was just his tester. Like that was just his floating the idea. Yeah. You watch this space now.
So I will be watching space as often as I can.
Oh my god.
Did you guys not realize it was going to be this hilarious?
Oh, that's the funniest thing.
Ding ding. Round 22.
Round 22. Fight.
In case it wasn't clear, I agree with Claire on this.
Oh my god, that is insane. Now, I will say that we are technically at the end of our stream. But I know that Andy has been trying to get Saturn for everyone just because it was so damn close. And I have been stalling for Noel, but I don't think Noel's going to be able to bring it to us. I'm not sure how you're going there, Noel. How are you going? Do you think you've got it? He's on mute.
I've nearly got it.
The problem is I don't know.
I haven't told anyone what you're trying to image.
Make sure that I find the right star.
Yeah. All right. So
I've got to make sure I get the right thing.
Can you explain to everyone what you're trying to get for us before we close things out?
Yeah, it's a star called RS Ophiuchi. I'm waiting for Neil and Claire to correct me on the pronunciation there, but
Ophiuchi.
it's
Well, a few.
Yeah,
I was
thank you very
close.
Yeah. Was it every 15 years or so it erupts, and it went nova this week. And so I was trying to, and so basically it got bright, and I was just trying to find that because I thought that might be an interesting point, but
It would have been, yeah.
yeah,
That's what I've been
not knowing
scoring for.
I'm trying to plate solve to make sure I can pinpoint which star it is, but it's certainly nothing as exciting as Saturn.
No, it's not. And we haven't got Saturn up yet. I know Andy's been
Not to
trying
look
get
at
Saturn.
anyway.
But I was trying because it's a really cool thing to try and see. We put out a post. Sorry, I'll rephrase that. Linda put out a post to the ASV yesterday giving directions on how to find it with binoculars or a telescope visually. So if you go to our Facebook page, you can see that and you can follow those instructions and you can try and see it visually with a telescope or binoculars from your backyard as a cat walks past Neil. How's your cat doing, Neil?
He's doing great.
So
Hungry.
It's a really cool thing to try and find. I tried to find it last night and I just couldn't. I couldn't get myself to, I couldn't work out exactly where I was. Not enough stars where I am, and the neighbor had their light on. Didn't help. So I will try again tonight because I know it's clear out there at the moment. But we have some instructions, step by step, star by star, sort of star hopping your way through on our Facebook page that I highly recommend you go and find and have a look at and see if you can give it a go. And I know Noel was trying to get that to happen, but it didn't quite work, which is unfortunate. And I don't know if Andy's managed to get Saturn up, but I can't see it on his little screen there in the corner. So I'm going to say that he hasn't been able to get it up.
I've got it on the guide scope, but I'm just still trying to.
Oh, there we go. We found it. And Gunnar, you are spot on. Who needs Netflix when you've got the ASV live streaming for you? I mean, really, is it Netflix and chill or is it ASV and chill? There we go. There's Saturn.
Oh, I finally found it.
Now,
Oh, sorry, Andy. This is even better.
that's all right. No, this is my guide cam. Just
That
wait a
looks like
minute. I'll
a
get my
photo.
main camera.
There we
Let's
go.
close it out with Saturn. I know that it didn't win, but it is so beautiful to look at. It really is.
It's a little bit out of focus, it seems.
It is a touch out of focus. It needs to be
Yeah,
sharpened up.
I haven't had a chance to focus yet. Oh, actually, I've still got it stretched too.
Don't stretch it. There we go. That's a lot better.
Always so
So we-
helpful, Mark.
I know these things. I should be an astrophotographer. I just don't
You
have
are.
the skills or the knowledge or the equipment. That's all.
He's an
Oh, rubbish. You've taken lots of
astrophontographer.
amazing
I'm an
photos.
astrophotographer. Yes, I am.
Astrophontographer, that's right.
Yes.
Yeah.
So this image here is something like what Christian Huygens would have seen Saturn when he described it as having ears.
I know people like that. They look just like that.
Adam Gilchrist. There we go.
Ears, Prince
Wallace,
Charles as
Wallace
well,
and
like
Gromit.
that.
Charlie.
Wallace
My
and
great uncle
Gromit.
Brian.
Your great uncle Brian.
Yeah, he looks like Wallace and Wallace and Gromit. It's great.
I was going the cricket angle, but yeah, Wallace and Gromit.
Wiggles the
Jeez,
ears.
Gromit.
Oh, there we go. There's a more
that's
focused
pretty.
version, Lee. It's not yours.
Yeah. Oh, look, it's the Barlow. I don't know where my back focus is at the moment.
That's all right.
It's my
Still pretty
excuse.
cool.
I'm sticking to it.
Oh, there we go. I've been
Yep.
lucky enough to be testing one of the ASV's telescopes
Oops.
since lockdown started, and that view there is about what I can see visually through this telescope I'm testing. It's quite a stunning view of Saturn and Jupiter as well. But I don't think you'd ever get sick of seeing Saturn through a telescope. It's just.
Can you imagine how much more boring it would be if it didn't have the rings?
Oh,
like,
it'd
it'd
be
just
very
be-
boring, wouldn't it? It would
it'd
just
be
be
a-
a tiny Jupiter.
Yeah, it'd be a beige ball with a couple of dark beige lines on it.
Yeah, it would be, absolutely. So I think we might close it out with the view of Saturn. I'd like to thank the team on the stream, Andy and Lee and Noel and Claire and Neil and Anne-Marie. And I know, Anne-Marie, I know you had a lot of technical issues tonight, but we all did. We had some pausing streams there for a while. I dropped out myself. YouTube was playing up.
Oh, you wouldn't believe the things that happened, Mark, while you were gone.
I'm sure a lot happened in the 10 seconds I was gone. But yeah, it's been one of those technical nights. I think it's one of those points where we're all sort of, the whole world is just done with everything that's going on, and it just went, nah, I've had enough. We'll have some technical issues. Thank you.
The gremlins have gone into lockdown with us.
Pretty much. Thank you to everyone on the stream for watching. To those who donated stars on Facebook, to our YouTube followers who put up with not being able to comment for a while. Not sure what happened there, but yeah, thank you everybody. We were meant to have an in-person event at Melbourne Observatory next week. It was sold out. I'm fairly confident that it's not going to happen, that we're going to still be in lockdown.
It could be very exclusive, just like one person. Maybe. It could be a very exclusive.
Very exclusive event. I'm very sure
Nothing's
that
stopping you from getting out into your backyard and looking at the sky, though.
No,
exactly.
There's not, but there's a reason for what I'm saying, that if the event is cancelled, and we're pretty sure it's going to be cancelled, we are going to be doing a live stream version of it on Friday night, and it will focus on the Melbourne Observatory and the Great Melbourne Telescope, and we will be looking at objects that the Great Melbourne Telescope imaged for research purposes, and a history of the Great Melbourne Telescope and the Melbourne Observatory, which is what we would have been speaking about in person at the observatory on Saturday night. But we're going to do it on Friday night, and I'm pretty sure that's what's going to happen. So keep an eye out. We'll pop it on Facebook. We'll promote it on YouTube, obviously, and for the members who are watching, we'll send it out to the members as well. But thank you, everybody, for joining us tonight. And thank you to the team tonight for bringing the objects to us live streamed as well. It's been a lot of fun, even with the technical issues. So we'll see you next time.
Bye.
See you later.
Ready, bye.
Bye.